Hello, everyone. Welcome to this workshop on P4 programmable switches. My name is Jorge Crichigno, one of the organizers of the event. This event is organized by the University of South Carolina, ESNet and the Engagement and Performance Operations Center, and the Great Plains Network. The event is supported by the National Science Foundation. And I want to start this very quick overview of what is this workshop, why do we do it, and how will this continue. This is a training workshop supported by NSF, and one of the reasons is the increasing trend towards programmability and open source that we have been seeing since over the last 10 years. This timeline is just an example, starting around 2007-8 with SDN, moving to Science DMC 2013, P4-14, P4-16, and more recently, research cyberinfrastructure such as Fabric, which we will hear today. So that was one of the motivation of the organizing team to prepare this workshop. We hope that this workshop will facilitate the adoption of programmable P4 devices by cyber infrastructure and IT professionals in general, and also will help integrate P4 material into all levels, associate, bachelor, and graduate degrees. You will see that we have developed some virtual labs on P4. We hope that these labs will be disseminated, and also best practices and other resources will be disseminated. That's the reason why we're bringing people from industry, from research infrastructures, such as Fabric, and also from universities. So the workshop website, you should have received this information and your email is provided here, and all the material, presentations, virtual machines, etc., will be posted in this website. The agenda for today, we have two main presentations. Then we will follow with two hands-on sessions. That is day number one. Day number two, we will have two main presentations. This is going to be a week from today. The first one, consideration for network performance and P4 campus. And then we will have also a short presentation, 15 minutes, TOFINOPod for teaching and research, followed by two hands-on sessions again. The material, you have access to the virtual platform. That access will be for 90 days, but if you want to extend, feel free just to email us and we will be happy to do so. Finally, we will be using for the hands-on material, we will be using a lab library that we built here at USC. It's about P4 programmable switches using a software switch that is called BMv2. However, during the length of this project, which is 4 years, we'll be developing many other lab libraries, including advanced topics, P4 programmable switches using real Tofino equipment, which is already built, but we will not be using in this tutorial, in this workshop. Network operating systems, and there are many more that we already built, such as SDN, OVS, etc. All this information is listed in the website, the web page that is here at the bottom. And again, if you want more information or wish to try these labs, just feel free to email us. With that, I want to introduce right now to my co-organizers. First, Jason Suraski. Jason is the science engineering engagement engineering at ESNet. He's one of the founding member of several open source software deployments, PerfSonar, O1, OSCARs, and many others. Before joining ESNet, he worked for the University of Delaware and Internet 2. So Jason, do you want to say some words?
Absolutely, and thank you, Jorge, for the great introduction. Representing myself and representing the Engagement and Performance Operations Center, we're happy to have everybody signed up and being a part of this event over this week and next week. We're here to understand and support all of the campus infrastructure as best as we can. So certainly ask lots of questions and enjoy the speakers as we go through the workshop.
Thank you, Jason. Another co-organizer is James Didon. He's the executive director of the Great Plains Network, a nonprofit or consortium, nonprofit organization of research universities focused upon connecting networks, advocating research, and cultivating community. Prior to joining GPN, he served as CTO for OneNet, Oklahoma's research and education network. For more than 2 decades, Didon has helped drive cyberinfrastructure initiative by working with leaders in Internet 2, regional and national initiatives. James, do you want to say some words?
Thanks, Jorge. Thank you for the introduction. Just a couple extra things. I just want to say I'm very excited about helping sponsor this workshop. As Jorge mentioned, GPN has been focused on research cyber infrastructure needs of the universities in our region, and I'm very happy with the level of engagement that the IT professionals at our institutions, and especially at our state networks, have in researcher success. And so given the focus of this workshop, I'm very happy to see the opportunity for those professionals to get more familiar with P4. And I'm especially excited about the spring. We'll be hosting one of the fabric nodes in the region. So we'll be able to have an opportunity to help researchers in that respect and have a better understanding of how they're leveraging that test bed. So thank you, Jorge, and looking forward to the workshop.
Thank you, James. It's a true pleasure to work with both you, Jason and James. And now I want to introduce the first 2 speakers that they will talk about Fabric. I want to thank you, both of you. First, Casey Wan. Dr. Wan has been a professor of electrical and computer engineering at Clemson University since 2004. His research interests include future networking and computer architecture, software-defined infrastructure, and artificial intelligence. From 2012 to 15, Casey was a visiting professor with Stanford University, the Open Networking Lab, and Big Switch Networks. From 2015 to 17, he was Clemson Networking Chief Technology Officer. Casey, thank you very much for being here.
Well, thank you very much, Jorge. Can you hear me well?
Yes, I can hear you very well. And I will introduce Paul also, and then I will let you share. Thank you, Paul, for being here. Paul Ruth is an assistant director, network research and infrastructure at the Renzi Institute at the University of South Carolina. He has been a member of Renzi Networking North Carolina. I apologize. During his time, he has contributed to several large computer networking and cloud testbed, including Genie, Chameleon, and Fabric. He received his PhD in computer science from Purdue University in 2007. He currently leads the advanced networking effort for Chameleon and is a member of the leadership team of Fabric. I should mention also that Dr. Wan is a member of the leadership team of Fabric. So thank you both, and I will let you continue with the presentation.
Sure. Thank you so much, Jorge. Today, I'm very happy to come here and see many friends, familiar names in the crowd, and also many new people. We're always happy to share what we're working on with the Fabric testbed. We hope this will be really a community resource. And I'm really excited to hear Jorge talk about all the P4 development that has been going on in the community. We're actually building up Fabric right now, and then all the elements that you have mentioned, the tutorials will be great materials to to work together to make it easier for researchers to conduct P4 research. So some of you may have already heard and known about Fabric for some time. Fabric is an NSF project. It started 2019. It's a mid-scale research infrastructure. It's meant to build a national scope testbed for future internet research. It's designed to be highly programmable and particularly emphasizing from the edge into the core programmable elements throughout the network. So this is led by a multi-university team. So other than Clemson, you have already heard Renzi at UNC Chapel Hill, Ilya Boding is the PI for the project. And then we have University of Kentucky, ESNet, and so Illinois, UIUC, we're working together on this. But then these are just the core members who drive this day to day. But Fabric is really collected, made possible by dozens of facility partners, university partners, science researchers all together. So as we introduce this, you'll see the many different elements that goes into Fabric's design and implementation. So why do we build Fabric today and as it is? So as in the past more than 10 years, actually, if I think about the NSF GENI project, GENI, Global Environment for Network Innovations, I believe many friends today in attendance will be very familiar with GENI. So GENI has been a national future internet testbed as well. It has been very successful, having large number of researchers leveraging that, students learning that in the classroom. One important element is that it is highly pervasive. It's a very big distributed cloud system that people can go in, reserve many entities at many locations, and then they're all connected through Internet 2 and the national and regional networks. So we can do a lot of experiments there, but one of the limitation is the computing capabilities of the GENI elements are limited. And that was influenced by 15 years ago, the technology, the economics available at that time, that's what we can do the best. But nowadays, because of the change in the economics for these elements, now we can have very large compute and storage capabilities input into compute servers. So what we're looking for as a transformative opportunity is if we can rebuild the whole internet with these very resource-rich elements, would we build it differently? Can we build a much more stateful internet where much more information is known and processed throughout the network to decide how the network should operate? So you can see that we incorporated at every node within the Fabric network. It'll have these computing elements like graphical processing units, GPUs, FPGAs. We're going to have lots of memory and lots of CPU capacity at every node. The network is also a very high capacity from 100 gigabit to 1 terabit per second, and I'm going to show you the national topology in a minute. So one of the important reason for Fabric is NSF sees the importance of supporting multiple research topics that has been catching national attention. So we really have a multi-dimension mission at hand. We have to not just build a network testbed, but we, at the same time, are expected to really collaborate with research communities in different topic areas. I listed some of those here, the very important high-level breakdowns. We have machine learning and AI researchers. They're really looking into how the network can become a big data instrument. So how can you really gather lots of network information and measurement in real time and use that to run network control algorithms or use that to optimize the network traffic going over that. And this is not alone in academics. This is already happening in the industry. We can bring up many examples of the industry trying to talk about how network will become really autonomous, self-driving going into the future. The second area we identify here, 5G IoT, that is really looking at an edge for the internet that is changing. So much higher amount of traffic expected, generated in a mobile fashion. And how can we make the edge much more aware of the traffic that is going over that. Science applications in all different topic areas. And we really make an effort to connect to all the existing NSF computing facilities across the country. So from supercomputing centers to campus computing centers, and then for all the NSF testbeds that have both networking, wireless, cloud. These are all elements that we're bringing them together. So really, we are thinking about the network as a computing continuum. So as we link all these different elements here, you can see in every part of the network, computing really is a major component that is being done, but at different scales and different form factors. With the fabric system, we expect to engage as we always think about all the different communities. How can we support different needs with the same infrastructure, which at the same time really push for the boundary of performance. It's really high capacity, high throughput, but we also wanted the programmability that go down to the very low level of visibility. So Fabric as a national programmable network, what we really wanted to the community to see that is it connects a lot of the elements that researchers may need to build interesting research topologies. So you can have existing production grade computing facilities. You can have programmable network elements, whether it's the smart NICs, the network interface, or whether it's GPU and FPGAs. And we wanted it to be very easily composable. So we really go out of our all the efforts to try to make it very simple. We see them as a lot of computing elements that we can connect them, just like connecting PCI devices. So it's becomes very easy to drag and drop all the only the resources that you care and put it into an experiment. So this is a topology that you can briefly see across 29 locations within United States. This is all on the Department of Energy or ESNet version 6 footprint. So all the yellow lines show the terabit per second supercore, that's how we call it. They'll have the very high bandwidth capabilities, but all the blue lines are the 100 gigabit connections. And these are all DWDM optical links that is, we're directly building our fabric nodes on top of this optical substrate. Important point we want to emphasize is this research network directly interface with the public internet. So we work with Internet 2 to pair with the public internet, both on the east and the west of United States. We also go through those pairing points to connect to the commercial cloud operator. So we have Google Cloud, Amazon, Azure. They're all going to be connected to Fabric. So that means you can set up a Fabric experiment topology to interface with the computing entities that you already have on these cloud platforms. So I want to mention Fab, and I see several of the Fab partners in attendance today. So Fab stands for Fabric Across Borders. This is an NSF IRNC, International Research Network project. It brings the fabric footprint beyond United States. So we work with partners in Japan, in Europe, which includes in UK, Bristol, and then we have our European partners, Amsterdam, CERN, and also we have South America with Brazil. I see Alex here today, I believe. So we are connecting through Miami to Brazil. So these are all the partners that we have specific science focus that is leveraging this international extension of fabric. So you can see from astronomy to high energy physics to urban smart city IoT research to 5G to P4 cybersecurity. So these are topics that we are helping researchers as the first use cases to bring them up on Fabric. So here you can see a rough illustration of what a typical Fabric site looks like. So every Fabric site contains multiple worker nodes, and we have these servers connected to a network switch that will go on to our 100 gig or terabit optical connection. So from a programmable networking perspective, we have different options. We have the P4 switches. Tofino was mentioned. We are working with Intel to have some of these switches available within Fabric. We're also looking at the FPGA side. So where Paul may talk a little bit more about that, we can implement P4 by an FPGA implementation, which makes it much more sliceable for supporting multiple experiments. And of course, because of the really powerful nodes, we can run the software P4 switches pretty effectively as well. So it gives the researcher multiple options. And every node, by the way, we call it a hank. Basically, it's the unit of textile. Since this is the Fabric testbed, we have these hank nodes that are deployed at different locations as our basic unit. So the Fabric node, we have these servers, the Dell servers. These are AMD with very big RAM, GPUs, FPGAs, very big storage. Every site have substantial storage, but at the same time, we also have two major locations with much bigger storage. So to researchers, really what it matters is you can design experiments to have lots of measurement. Those measurements will be easily stored within the Fabric system. And then once you complete your experiment, you can export those measurements for your research purpose. We have the Smart NICs in addition to the P4 switches. The Smart NICs is the Connect X 5 and 6. You can emulate SDN, software-defined network, using those NICs very easily with your own controller. And then we also have DPDK. We're going to run that on the Fabric nodes for increased performance. So one emphasized point for Fabric is the measurement support. So we have a measurement substrate. It has its own measurement network that is going to transfer all the data that you're measuring. And then there's a wide range of measurement that a researcher may want to use. Some of the examples here is we have GPS discipline clock at every node. So that means you have very, very precise timestamping capable. And then those will go into all the packet traces that you collect in your experiment. You can have port mirroring. You can measure the power in the compute servers. The optical layer have some limited measurements available as well. The building blocks for Fabric, for those familiar with a network testbed like Genie before, you will be familiar with the term slice. A slice is basically a collection of different network and compute resources that can be tied together into a network topology. So we use slice as the unit, and then within slice, every resource that you include is called a sliver. And one of the important design feature for Fabric is we expect experiments to evolve over time. So once you create a slice with some topology, later on, you may want to add new nodes, new network elements, or you want to expand it. You can add that, and you can change. You can remove things from the past. So that is a very important change from what Genie can do in the past. And then the underlying connections, we expect most researchers wanted these layer 2 connections between every node. We use MPLS to achieve that. And that is permanently configured using IPv6 on Fabric. So there's a stability benefit there to have these MPLS layer 2 as the element to compose the topology. You can have with and without quality of service support. Both are possible within Fabric. So now I will talk about some topologies. We expect many experiments may want to have these bumping the wire configuration. So you can see under this graph where you have layer 2 connections going in to one of the network interface, and it comes out what behind the NIC is actually connected to a PCI interface that go to the storage. That means packet logging. So you have the packet trace very quickly captured, stored, and then the GPU connected there can immediately process those for machine learning type of problems. You also have the GPS connected to those elements so that you can do the timestamp very quickly. So now, if I swap that to be FPGAs, think about these FPGAs can be just emulating an Ethernet switch, or it can be a P4 switch. Coming in, you have these connections, again, going to the PCI and can be logged in different ways. And multiple FPGAs can be streamed together to become a larger switch, or it can be a pipeline that you compose. One of the things that we spend a lot of time working on is to make it easy for you to have your own FPGA binaries running on these code. So we worked out a solution. So at the Fabric site will have the ability to run the FPGA runtime, while individual researchers, you can have your own license to compile those binaries and load it onto the FPGAs. So this is additional slide talking more about how the storage is arranged. It's really a tiered architecture with different levels of storage, all the way from the spinning disk to the solid state drives, SSDs. After this, for the AI/ML, what I want to mention is the ability of the GPUs. So again, is connected as through PCI interfaces. So there's a lot of different processes you can run on that. And external facilities. Now, this is one emphasis that we have it from day one of the design. We want to make sure that external facilities can be connected either as a layer 2 network connected resource or through a layer 3 network. And this includes all the supercomputing centers, or it can be the cloud testbeds. With our international partners, we connect to their Fabric nodes or their campus resources this way. So pretty quickly, we're going to talk about, okay, so this is the public cloud. So we have a topology with Internet 2 to get this happen. I think a lot of details, we will be sharing that with the community as we turn these on. So today's focus is on P4. Let's see. Here, this is the individual researcher's laptop. It's just like any other external facility we can connect that. But I want to quickly go to the P4 part. This is an indication of the measurement concept, how we do that. There's different sort of software that people may be familiar with, Elasticsearch, Kibana. These are all the provisioned in the Fabric services, whether the Fabric system itself and the Fabric experimenters can all use this. Okay, so from P4 this point on, I think I'll hand it to Paul to talk about that. There's really multiple different ways that we can compose this, and Paul will walk through a few of the examples that we have already been working on.
Cool. You want to unshare and I can share?
Sure, I think you can do that now.
So this one. This one. Share. Boom. All right. So everyone can see this, I assume. All right. So as Casey said, my name is Paul Ruth, and I'm at Renzi, UNC Chapel Hill. And one of my major roles with the Fabric testbed is to collect, to manage the users and collect the users' requirements and try to figure out how to get that running on Fabric, and vice versa, teach the users how to use the various capabilities that Fabric has. And for this particular audience, I'm going to talk about the P4 work that we've been doing, trying to set it up and get P4 started on Fabric. So as Casey mentioned, the main purpose of Fabric is to allow you, the user, to control things in the core of the network at scale with high performance links and compute and so forth. And an example experiment looks like this. You might have various different types of resources and nodes that you want to have in various places throughout Fabric, and you can connect them together with these high-speed links. What's interesting here is you can compose things together. So there's some external resources and FPGAs and GPUs and SSDs and so forth, along with P4 switches, all the same thing. For the purposes of this talk, we're going to really focus mostly on the P4 parts, but keep in mind that all these other stuff is available, as well as you can compose these slices with P4 switches along with other things. So you can think of doing interesting things where you have maybe a P4 switch, but then you have a GPU doing some AI that's controlling the program, how you're programming the P4 switch, and all in the same spot in this core of the network. So keep that in mind when I'm talking about this, that I'm going to focus on P4, but there's really more to it as well. So Casey showed you this slide as well. This is the picture of our 29 sites that we're funded to build in the United States. Of course, he mentioned that there's some outside of the United States that we're also funded to build. What you're going to be able to do with these sites is request resources at any of the sites, or all of the sites for that matter, and then connect them together with dedicated layer 2 circuits between your resources that you've allocated at these sites. There's lots of sites, terabit links, 100 gig links. We control them at layer 1, so we can give you layer 2 circuits. Often there'll be quality of service, bandwidth guaranteed, things like this. And then the other thing that Casey mentioned is really important here is that it's connected. All of this allows connections from within Fabric's resources to outside. So you can see a bunch of cloud resources like Chameleon and Cloud Lab, as well as the public clouds like Google and AWS and such, as well as it's connected to a bunch of other test beds, including Powder, Cosmos, and the different power test beds, and a lot of supercomputing centers. And one thing that's not quite mentioned here is that we can connect to your campus. So if you have something in your campus, if you have Internet 2, Layer 2S, these kinds of things, we can connect your resources and your instruments to all of this and expand what Fabric can do. And we'd like to do that. So as far as P4 is concerned, what we're gonna do is allow you to deploy P4 switches at any or all of these resources and connect them with your definition of your topology that you would like to build. So in this case, I have this picture. I just kind of randomly picked some of the sites, and we're gonna pretend that I have a slice that has these. How many did I put here? 7 P4 switches that are strategic places across the US. And at some places, I'm going to have a link out into Chameleon, where I might have a giant compute cluster, or Cloud Lab, where I have another one, or Azure or AWS, where I might have some more public cloud resources, and potentially in my institution or your institution and your collaborators' institutions as well. So think of it, this is really what the power of Fabric, and what this is going to allow you to do is you're going to be able to do your P4 experiments as if you owned the core of the internet. And you're going to be able to create your own ideas about what the next generation's internet should look like, and you'll be able to deploy them and test them in a scaled, in an environment that allows you to scale your experiment to, at least the US, probably the world, and get really high performance as well. So this is really what we're offering. The challenge for us, I guess, is to figure out how to allow you to have these P4 resources, these places where you're sharing them amongst yourselves. Like, you're not going to get this P4 switch at a strategic place forever. You're going to have to share it with everyone else, kind of like a batch scheduling kind of style, or like a cloud resource, but it's a network resource. And as such, we're going to have different types of resources at these sites, and you're going to ask for the different resources that you want for your experiment. Could be software switches, as Casey said, could be Tofino switches, or we'll have some Xilinx FPGAs that can act as P4 switches. So we'll go over those just a little bit. I mean, everyone knows that what everyone wants when they say P4 is they want the Tofino switches, but those aren't yet available in Fabric. These, when we do have them, there will be dedicated Tofino switches sitting in these racks at I think maybe not all the sites, but most of the sites. And you will be able to use these as if you own that switch. So you'll be able to insert your compiled P4 program onto the switch, and you'll be able to connect to it and connect your controller to it and control the Tofino switch as you would if you owned it. And you can have them, several of them all across the United States. Currently, the initial hardware, the Tofino hardware is being acquired. We're trying to buy them and find out who will sell them at the best rate, and then has them available right now, for example. This is a little complicated because there's licensings and NDAs and stuff involved with Tofino and Intel, and trying to share these proprietary resources is a little tricky. So we're still trying to work out the workflow that is going to be used. I imagine Jorge and the people designing these tutorials that you're going to do today have similar challenges that they're seeing. The next one, so one of the things about Tofino that is actually challenging as well is that you can't share the Tofino switch at the same time with multiple users. So if we have a switch and you want to use it, we have to give the whole thing to you for that moment. And as a way to provide more P4 switches, more hardware P4 switches to users simultaneously, as well as to just reduce the cost. And there's also some reasons why you might want to use an FPGA-based P4 over a Tofino one in the first place. But what we're going to do is we're going to have Xilinx FPGAs, which are currently also not yet available. But you can use these as a small port count P4 switch. The Xilinx folks have some extensions to their FPGA toolkit that allow P4 to be deployed on it in a fairly simple way, but it's not perfect for Fabric yet. So we've been working with Miriam Lesser, who's an FPGA expert at Northeastern University, and she and her team are going to help build a Fabric bitcode for Xilinx that will provide the needs that our users are desiring. If you have some special needs for this, let us know. There's still time to get some changes in there. So if you have some interesting FPGA Xilinx P4 needs, let us know. Yeah, and so this will be available at some point in time. And what is available now is mostly as an initial deployment of P4 so we can get it started, but it's also going to end up being a great way to have educational resources for lots of users that can simultaneously use it, and for just development of P4 programs that can be deployed on the Fabric infrastructure are the software P4 switches. So I think some of the classes that you're going to take later today and in the next sessions are based on the BMv2 model. So this is, you can think of it a little bit like a software-based P4 switch. It's open source. There's, you can go to GitHub and download all the code for it. And what we did to get P4 started on Fabric was we took the BMv2 switch and packaged it so that we can deploy it in a VM on Fabric and connect it to these to the NICs that are connected to the wide area dedicated layer 2 circuits that you can provision. So So now you get a VM with PCI pass-through to these hardware NICs that can get really high bandwidth and dedicated layer 2 circuits across a wide area. And now you have your BMv2 switch that you can control and program and configure as any way you want. We also have Jupyter notebooks that will help you deploy these in a very simple way. Hopefully simple, as we get better as we get better users and we get more feedback from what the users actually want. We can improve that. And also interesting is that we've been working with Intel and Tofino and Barefoot and trying to get the Tofino native architecture to learn more about it, because we're going to be deploying the hardware Tofino switches. And they have something that's very similar to the BMv2 model called Tofino native architecture, Tofino model. And we can do something very similar with that, although there's Intel NDAs required for this. So unfortunately, I can't give you the software to do this. But if you have access to it on your own, I can help you use the Tofino model in place of BMv2 on top of Fabric resources, but you have to get the software yourself. So it's an interesting twist here. I think they're working on making it more widely available, but we'll get there. As an initial example on what we're to try to share this with our users and get people started, I first had to learn P4, so I went to the P4 Lang tutorials that many of you have probably seen. They're probably very similar to the tutorials you're going to take today, although I don't know what tutorials you're going to take today. These are a great place to get started with P4. They have a lot of hands-on exercises, a GitHub repository with not only the software you need, but the exercises and an incomplete version of a P4 code, and you're supposed to complete it and solve the challenge. As you can see here, this is just a screenshot of their GitHub repository. They have a whole list of exercises you can take. The interesting thing is the way they do this is that they have a virtual machine that you can use, and that virtual machine uses a combination of Mininet and network namespaces and such to deploy a topology that most of these exercises use that looks like this topology here, which is 3 P4 switches in a triangle, and each one of the switches has a dedicated layer 2 circuit between it and the other 2 switches, as well as a link to a local node that is like the host that's connected to that switch. And what you do is you do the exercises, and the second one is maybe one of the more interesting ones, or the first interesting one. And what they walk you through in that case is how to make a custom tunnel that'll go through these switches between this host number 1 and host number 2. And it's pretty interesting because you log into the where the switches exist and their BMv2 model exists, and you can rewrite the P4 program and compile it and deploy it, and then send packets through, and you can see them make it to the other side or not, depending on if you did it right or not. So this is their P4 tutorials, and they're pretty solid. One interesting thing is your next speaker is Vladimir. There's a bunch of videos out of him actually teaching people how to do some of these tutorials, which is really good. And I've actually been taking some of the Intel classes on Tofino P4, and he's teaching that and doing a great job as well. So we'll enjoy his next talk. So go out and watch the YouTube videos and do these P4 Lang tutorials. So what we did as an initial challenge here was to take the P4 Lang tutorials and just move them to Fabric. And the idea was to use the exact same tutorials as the P4 Lang tutorials, but replace what they have, what they're using Mininet, replace it with actual real Fabric resources. So we did this, and we can make it work. We have a Jupyter notebook that uses our FabLib library. So the screenshot in the back here is a screenshot of a Jupyter notebook that I wrote that has that'll use our FabLib Python library to deploy a Fabric slice that has in it the BMv2 software switch, as well as the P4 Lang tutorial repository, just cloned straight from GitHub. And it'll set up this particular slice here, which is the exact same slice as we saw before in their tutorial, where you're actually going to have 3 P4 switches anywhere. You pick any 3 sites in Fabric that you want, you can put them there. It'll stand up a BMv2 software switch and create dedicated circuits, layer 2 circuits between them in a triangle. And then you can create a second VM at each site that is the host and connected into the switch as well. So now every switch has 3 ports on it and is connected to one host, right? Yeah, so now what we have basically is individual BMv2 switches using any Fabric site, dedicated WAN L2 links between them that look exactly like the L2 LAN tutorials, and a Jupyter notebook that will deploy them. And this, when you log into Fabric's portal, you can launch a Jupyter Hub instance or Jupyter Lab instance for yourself that will include these tutorials for you to use. So this is what we have. You can then, once you launch it, if you wanted to, this is kind of just to show our Fabric portal. We have a Fabric portal that allow you to view your slice that's up. In this particular slice, I was planning on doing a live demo for you today, but as you can see in this thing, and in this screenshot of our portal from over the weekend, there's disruptive maintenance from 2 days ago until next week. So right now the whole test bed is down, so I can't really do a live tutorial, but or live demo, but I was going to do that. But here's a view of the slice that I ran on over the weekend. It has the big gray boxes are, each one of them is a different site. And I think we have, it's kind of small, but it's Max, which is at University of Maryland, called Mid-Atlantic Crossroads. TAC, which is the Texas Advanced Computing Center in Austin. And then down here is Utah, which is the University of Utah. And at each one of these sites, there is a white box, which is a node that has the BMv2 software switch in it. And then another white box, which is the host. And they're on the same site, and we're connected with a local network there in the gray box. And then they're also connected to each other with these wide area network links that go across between Texas and Maryland and Utah in a triangle, right? So this is actually a live slice that I stood up the other day that demonstrates that. And what this looks like, if we go back to our previous picture of the whole model, or the whole infrastructure, is we have you have, using our Jupyter Hub environment in the notebooks, you can just launch a slice that looks like this. And what this ends up being is, I feel like I'm repeating myself, but it's interesting that to see it from different levels, I guess, is a P4 switch at the University of Utah, a P4 switch at the University of Maryland, another one at TAC in Austin. And they're connected with dedicated layer 2 circuits that you control, and you're not sharing with anyone else. And they each have a local host that's also in that same rack. And on top of all of these nodes is both the BMv2 software as well as the P4 LAN tutorial. And this is the topology that the tutorials use. So you can do things like build your basic custom tunnel, but now instead of going between one half of your local VM to the other half of your local VM, it'll actually go from a host sitting at the University of Utah to a BMv2 software switch also at the University of Utah, across a dedicated link across the country to another switch that you're controlling with P4 at the University of Maryland, and then to that host there. And so this is pretty powerful, and it's a good way for people to start learning about P4 by using these really simple tutorials, as well as to learn about Fabric and how you're going to embed P4 into Fabric eventually. It's worth noting a couple things here, like that the difference between this using the BMv2 software switches and the Xilinx and Tofino hardware is pretty small. I mean, it's big in terms of like how fast the hardware can go, and like the difference between the Xilinx and Tofino is going to be pretty different in terms of how you code it. But in terms of deploying it on Fabric, it's going to be pretty straightforward to just change to your Jupyter notebook and the using the FabLab library to deploy different types of switches here, depending on what you want to do. So, and also the Tofino models software switch is possible. So if you have this code, I can show you how to drop your version of that code into one of these switches, and you could actually have the Tofino, the Tofino version of the P4 model running over here and do the same tutorials, but with Tofino. Yeah, and then what's also interesting here is like you can do all of those tutorials that the P4 Lang has provided, the P4 Lang organization has provided on their tutorial repository on GitHub. And you could, in fact, do even more advanced tutorials that, like, for example, some of the ones I'm learning about by going through the Intel Tofino P4 coursework or classes. I could deploy them on here and run them across the wide area. Of course, and they'll be slower, of course, but that's the trade-off for now. In summary, so P4 experiments on Fabric. What the goal is to put user-controlled P4 switches in the core of the network and connect them with dedicated layer 2 circuits. Hardware, P4, Tofino, and Xilinx are coming soon. Software, BMv2 and Tofino are both possible now. The BMv2 version is like fairly simple to deploy if you get an account, and if you have an account, and you can just run the Jupyter notebook and it'll bring it all up. And we have this whole set of Jupyter notebooks that'll streamline it all. The other thing that is not in here that is important to know, and I mentioned it briefly before, is that one thing that's really interesting about this is not that you're just, it is interesting to have P4 switches just spread out all over the country, connected into your own internet, basically, but you can combine them with all of the NVMe storage and the GPUs and the other accelerators we have at various places to actually control your P4 network in ways that you might not have thought you could. Like if you wanted to have, like my example of using the GPUs to do some AI to reason about how to change routes or something like that. And then also you could use the storage to maybe have a caching mechanism for some content distribution network or video streaming or what have you. And you could maybe use AI to do that too, I don't know. So the idea is to combine this all together and use P4 to control the network. And the other thing to keep in mind is that we do have quite a bit of power inside of Fabric, but the amount of like just compute power for the edge it's not just limited, but like there's just better places to do it. And that's one of the reasons we think that it's pretty powerful to connect all these Fabric experiments to things like Chameleon and Cloud Lab and Amazon and your own your campus or your collaborators' campuses and things like that. So yeah, I hope that's a pretty good summary of what we got going on. I guess we have, if you have any more questions, we have some websites, we have some documentation. I think probably, although we're still in the phase where we have beta testers are on Fabric and we're not truly open to the public, I think some of the P4, like I don't know that we have anyone doing really interesting P4 work as the beta tester. So if you have some interesting P4 project that you want to do, please contact us, and especially if you think it'll map to Fabric well, we might want to work with you to figure out what kind of capabilities we should provide, but also maybe to get you to try to start using things and beat on our P4 capabilities for a while and see what breaks first. So yeah, I think is that it, Casey? I think that's the last slide.
Yep.
Yep.
That should be it.
So I guess we have a few minutes. I don't know if you want to do questions or what.
Thank you both. Thank you, Casey and Paul. There are a few questions. Some of them were already answered here in the chat window, but I want to bring the first one by Asael. He said, are there plans to extend the network to other national research and education networks? Alex already answered. Thank you, Alex. But in general, let's say an institution here in the US want to extend. What are the requirements to extend to become a node?
Become a node? Do you want me to answer, Casey? Or you?
Either way. So earlier we mentioned about the Hank. So each basic a Hank is like a rack of servers. For a US campus, it's very straightforward. If you have some projects with the resource you want to sort of grab, purchase a Hank node, we can share the exact configurations. Right now, some of the locations can connect using Internet 2 with AL2S. It's very straightforward to connect into the Hank, the fabric topology. But if you have even better than AL2S connectivities, for example, you are on the DOE side, we may discuss better optical options to connect your fabric. For internationals, all the current sites, we're only limited because of the IRNC funding. So we have to choose some sites to begin with. But the method is pretty flexible. So in most cases, there are already international network collaborations where NSF already have a funded circuit, an optical network connecting to that country. So in that case, as long as we can identify the points where that international network connects into US, we can work with the partner and then discuss what's the best way. For example, I mentioned Brazil. So we are currently connecting through an existing international network into Brazil, but Brazil at the same time are planning for installing additional fabric nodes at possibly different multiple locations. So if that happens, then we will just expand it pretty straightforwardly.
I'd add too that there's kind of two ways that you might want to connect to fabric. One is if you to have your own fabric node, your own Hank, that and that's powerful, especially if you have a campus where you might have several different research groups or instruments or compute facilities or whatever you have at your campus. You have a Hank, and then you can connect all those things through one Hank. But if you have your own research group and just your lab and you want to connect from your university to whatever the closest Hank is that already exists out there, that is also a possibility. And I suspect there'll probably be more of the latter. But of course, we want the former because it's, expands their footprint even more, right? Yeah.
Right, thank you. If you have any question, please feel free to write down here in the chat window or unmute yourself. I think the other questions were already answered. Okay, there are no other questions. So again, Casey and Paul, thank you very much for this talk.
Sure, thank you.
So we're almost 2 p.m. Eastern time. I will introduce the next speaker. The next speaker is Vladimir Gurevich from Barefoot Networks, Intel. Vladimir is the principal engineer at Intel and the director of Intel Connectivity Education Hub. Before joining Intel, Vladimir was a technical lead at Barefoot Networks. Vladimir also worked as a technical director at Broadcom. And before that, he was a senior manager leading the software applications engineering team. He was also one of the founders and key contributors to the comprehensive engineering training program at Broadcom. He worked as a software developer at Cisco System before and other networking companies in Silicon Valley. Vladimir received his master's degree in applied mathematics at Moscow Institution of Radio Engineering, Electronics, and Automation. Vladimir, thank you very much for being here. I was one of his students, and it was a true pleasure to learn from Vladimir.
Thank you very much. So I'm very glad to be here. Let me try to share my screen. I will just say that I'm a little bit worried because looks like you guys already started to discuss a lot of specific applications and deployments of P4, whereas my presentation is probably a lot more at the beginner's level, but that's what Jorge told me that might be useful. So that's what I would like to talk about, really. I hope you can see my screen. Specifically, I would like to give you a brief introduction into P4, and actually before that, we'll talk about data plane programmability as well. Okay. So here's the stuff I would like to discuss. First of all, why do we need programmable switches and what we can do with them? Second, we'll talk about how to build those programmable switches, and specifically, I will say a little bit about how they are built inside. Then we'll talk about how packet processing algorithms, so-called data plane algorithms, can be expressed, and that's where we'll discuss P4 language. And then I will kind of give you some next steps if you would like to proceed into that direction. So where to get help, how to sign up, and do all kinds of interesting stuff. And hopefully we'll still have some time for questions and answers. So I will start with an interesting premise that, of course, many of you do networking, but a lot of people believe that networking is kind of done. There is very little innovation in that area. And to a certain extent, I understand why people might think about that, is because there are a lot of standardized protocols. And if all the protocols are standard, where to innovate? But in reality, there is still a lot of innovation happens. There are just somewhat different drivers there. So the nodes, of course, are connected through internet using our standard TCP/IP protocols. But what happens inside large-scale data centers or big ISPs or inside government institutions, there is still a lot of innovation going on. There are a number of drivers for that innovation. People try to build systems on the scale that they have never tried to do before. They want systems which have a lot more flexibility. That's especially true about the cloud providers. They are looking for energy efficiency, and they are trying to replace a lot of legacy protocols with the Ethernet. So there is still a lot of innovation going on, but what is true is that this innovation happens at a pretty slow pace. Why this is happening? Well, if we think about our standard computing infrastructure, then innovation happens very, very quickly. And it is available pretty much to everyone, right? So all you need to do is you need to buy some computing device, depending on what kind of projects you have. It's all available to any student at any university. You can buy a small embedded board like Raspberry Pi. You can buy a computer. You can, at the end of the day, just run a VM in the cloud. You write a program in your favorite language. It could be big program, could be small program, and that's it. You can deploy it. You can even profit. It is a very, very short development cycle with tons of tools and very well supported and understood. In the networking world, things are very different. If you want to do anything at a real speed, at the real scale, you need to go to a company, which we typically call them OEM, companies like Cisco or Arista and so on, and ask them to build a new networking device that will do whatever you want to do, how you want to organize your network. And this company will tell you that actually they would love to build you such a networking device, but they can't, because these devices use ASICs produced by companies like Broadcom and NVIDIA and so on. And so they need to ask the vendor of these ASICs to produce the ASIC that will implement your custom protocol or your custom feature. And it takes a year or two, assuming that this vendor agrees to do that. And by that time, you know, your idea went away, you probably decided to go into machine learning or something. So very, very difficult to innovate in the area of networking. Why this is happening? Well, if we look at the architecture of standard networking device, they typically contain three classes of algorithms. The data plane in the bottom, these are the fastest algorithm, which really determine the feature set and the performance of the device. Then on top sit the control plane algorithms, which populate the tables and basically give the directions to this data plane algorithms. And at the very top sit the management plane. And so while these two top layers are typically programmed using standard programming languages and executed on regular CPUs, it is the data plane which is really problematic. And as I said, unfortunately, it is the key to the whole system performance. If you cannot get things done in the data plane, they will be done very, very slowly, because modern CPUs are no match to the speeds of our modern networking interfaces. And so people who design network equipment, they experience a huge challenge, because they definitely have tons of skills and they know how to write these two upper layers. But when it comes down to implementing things at the bottom, at the data plane, implementing the algorithms which are responsible for processing each and every packet that enters the telecommunication system, up till very recently, they had a very poor set of choices. Essentially, they had to go and use fixed function ASICs, which were very fast and could do things very quickly and at high performance, but they only had a fixed set of algorithms that were basically baked into the silicon. So anytime you wanted to ask this chip to do something unusual, something non-standard, basically the chip will say no. It will point you, or the engineers will point you to a set of data sheets which explain what kind of algorithms were put into the silicon. And besides what was there, nothing could be done. So that is really the problem that I try to describe. That is what stifles the innovation. And unfortunately, there was no real way to replace this ASICs, and there is none right now. So if you look at the performance, what you can achieve using really programmable solutions like general purpose CPUs or network processors of PGAs, this performance is a lot less than what you can do in a switching ASIC. So there was really no way out. And what we decided to do, and I come from a former startup called Barefoot Networks, we figured out that this is not the right thing, that the developers should have full control of their systems, and they should be able to process packets the way they want at the same speeds that can be achieved using fixed function components. And so that led to the design of the P4 language and also the programmable ASIC, the first programmable switching ASIC called Tefino, which supports that language. So that way, if you have an idea how you want to organize your network and you understand what kind of control and management plane you can build, you can also express the desired data plane algorithms in P4 language, load them on the ASIC, and instead of having any kind of failure, you will have an OK, and the ASIC will do exactly what you want to do. And if you think about that, that's actually a very, very typical scenario that we went through many, many times over as we were developing our digital technologies, right? So initially we had fixed function devices like, I don't know, arithmometers or stuff. And then of course we came up with CPUs, and we have all the high level languages that can be compiled, and we can load these programs on the CPUs, and that looks completely normal to us nowadays, even though about 70 years ago, it was something very, very unusual and unheard of, right? Later on, there was a time for the graphical processing using GPUs, Again, for them, there's way to abstract the processing that happens in these devices. Again, this language can be compiled. It could be OpenCL, it could be CUDA, but in any case, you go from fixed function devices to programmable devices. Same thing happened a little bit earlier in the world of DSPs, of course. It is happening now in machine learning. And so the real problem was that until Barefoot kind of came along, it was not quite clear what to do with networking devices. And why? Because they have a somewhat unusual architecture, quite different from those processing units that I just described before. And so what we have right now, of course, is that we have a family of Tofino ASICs. Now we have 3 there already, Tofino 2, and Tofino 3. We have a language which can describe the algorithms that we run there. It's called P4. There is a compiler. If we talk about Tofino specifically, there is a compiler called BFP4C, which can compile programs written in P4 onto Tofino. And what we get as a result, there are tons of advantages, obviously. So first of all, you get full control over the features you can put into the data plane program. You can control the table scale. You can also use P4 to describe your data plane algorithms very formally. That as a result, you can also do formal verification of these algorithms. What's interesting is that by controlling how your algorithms are compiled on the platform, you can also control the energy efficiency of these algorithms. Sometimes different choices that you make in terms of how you code the algorithm can affect that energy efficiency. And a lot of big scale cloud providers now are looking at that very, very closely because the energy that their switches consume is a big part of their overall energy budget. It all obviously became a lot advantageous to the companies which produce networking equipment because now they can build a single box, same way like we don't think about that, right? But you buy a laptop computer and you can use it for all kinds of things. You can write on it, you can process photos, videos, play music, and do tons of other stuff. With switches and telecommunications equipment, up till now, it was not the case. If you wanted to buy a switch, you buy a box. It looks exact same as a box, which is a load balancer, but this is a different device. It probably has a different ASIC inside. And so people were ending up having a lot of this network equipment, which could be used only for one specific purpose. One would be a switch, another one would be a router, another one be a load balancer, a firewall, and so on. Now you can build a single piece of hardware and use it for all these things, either together or just depending on what kind of program you can load in it. Programmability also made it practical to do tracing and telemetry, because now we could control which kind of results we can export from our data plane programs, and those results would start making sense. And of course, innovation-wise, we can now implement a lot of non-standard cases. We can use the ASICs not only to do routing and switching, but we can use them to perform load balancing. We can use them to implement network caches, perform in-network computing, accelerate machine learning, and do all kinds of things that were not possible before. And there are many other advantages as well. One is very important, is that this is your program, same way how you can choose what to do it, what will be the conditions under which you release the source code. Now you can do the same thing with your data plane programs as well. And this all became reality around 2016, 2017. So, well, now you can think of this as a whole century, 5 years ago. But you could see there's a picture of two boxes. You can barely tell which one is which. One uses a fixed function ASIC inside, another one uses programmable ASIC. And in reality, the results that you can get on the programmable ASIC are even better than what you can get on a fixed function one for pretty much the same price. So now it became a reality. And already I saw in the chat that you were discussing about buying a box, probably from the same manufacturer we have this picture from. It's EdgeCore. So I'm really glad that you came to this place. Now, question is how this became possible, because for a long time, people thought that this is something that cannot be done. The common wisdom was that if you try to build a programmable device, it will be much more expensive than a comparable fixed function ones. And so I think one of the insights that we had is that if you actually try to dissect a typical switching device, you'll realize that a lot of the silicon area used by a device is not used by the switching logic. So pretty much every device you can take, about 30% of the area is spent by something that is not related to the data plane algorithm at all. It is basically connections, MACs and SerDes. And then if you look at the remaining area, most of it is spent on memory and tables, for memory which is used for tables or packet buffers and maybe TCAMs as well. And fairly a small amount of that area is used by the packet processing logic. Now, when you build be this device programmable or not programmable, really, it does not matter. You still have to have memory. And the more we go, the more people want to put memory on the device because they want the scale to be better. And the logic occupies kind of fairly fixed amount of space. And so as technology progresses, it occupies progressively less space. So even though we might need more logic overall for a programmable device, even if this 10% of logic, we increase that amount like 2x, it is still a relatively small amount overall, a very small penalty overall that we need to add to the device to make it programmable. That's why we believe these solutions are so advantageous. And so, as I said, this became a reality. So around 2016, we built our first chip that was Tofino, a 6.5 terabit device. It has 260 lanes of 25 gig SerDes, so that's basically 260 25 gig ports or 6,500 gig ports. And ultimately, in price and in power and in area, the device was equivalent to the comparable fixed function devices as well. And then in 2019, we built Barefoot Tofino 2, which has twice as much bandwidth, and the ports could now go to the speeds up to 4 gigs per second. The device also got additional capabilities, so it became smarter. And then just recently, I didn't put a slide for that, but we announced the device called Barefoot Tofino 3, Intel Tofino 3 now, that has twice as much bandwidth compared to Tofino 2. So it's 25.6 terabits per second. Okay. So let's talk about how these devices operate, what's inside. So there are a number of insights that helped us to implement those switches, design them, decide what to put inside and what not to put inside. So overall, we believe that data plane algorithms are fairly simple, and they're limited to kind of 3 general classes of operations. So first of all, you need to be able to manipulate packet headers. That's what we typically do in the data plane. Secondarily, we need to be able to manipulate the switch state and interface with certain external components. And I will explain what they are in about 5 minutes. The other thing we realized is that a lot of operations that are required for packet processing are easily parallelizable, both in theory and that they have to be parallelizable. Mostly, this observations comes from a very simple fact. We are processing packet headers. These headers have many fields, and usually these fields are processed fairly independently. Last thing, and that is really not our observation, that's how these systems have been built for a long time, even in the fixed function world, is that really they are built around long pipelines. So all this came to brought us to a notion of the so-called protocol independent switching architecture, and that is an abstract model of a packet processing inside a high-speed device that serves as a basis for P4 language as well. So this model consists of 4 key components: programmable parser, programmable match action pipeline, and programmable deparser. So the match action pipeline consists of multiple stages, and each of the stages performs the same, fundamentally the same operation. It performs a match using some packet fields or intermediate results, and then it executes an action. And then all these stages, which constitute this pipeline, are connected together with the data, with the header and metadata bus. So the difference between programmable devices and fixed function devices is that in case of fixed function devices, it's pretty much the same structure, except that all these components are fixed and the algorithms are baked into the silicon. And in case of programmable devices, they are flexible and can be programmed. So how do these pipelines work? So first of all, the packet comes to the programmable parser, which is typically expressed as a very simple finite state machine. And what this programmable parser does, it splits the beginning of the packet into individual headers and their fields. So it can extract an Ethernet header with the destination MAC address and source MAC address and the Ether type. It can extract IPv4 header and so on and so forth. And whatever it doesn't process, it doesn't extract, is the packet payload, which will be traveling separately and will not be processed. That's one of the important things that separate, for example, switches from the NICs. NICs, as the endpoints, typically receive the whole packet, then they get to the CPU, and CPU can do whatever it wants to do with the payload. Switches typically ignore the payload. And that gives us a lot of advantages. First of all, the algorithms are a lot simpler. And secondarily, we can start processing the packet while the payload is still being received. In fact, we can even, on Tafino, we can even finish processing packet headers before we receive the end of the payload. So the header fields go into this match action pipeline. And there, as I said, we perform the same operation. We perform a match, for example, we'll match the packet based on the destination MAC address or destination IP address, and we can perform an action. For example, we can set the egress port, or we can decrement a TTL. We can do a lot of things. And we can continue doing that, adding headers, removing headers, changing headers or their fields, that is, producing intermediate results for as long as however many stages we have in that pipeline. And so that is one of the bigger differences between networking devices and corresponding CPUs, because in the CPUs, you can process data for as long as you want, maybe for a second, maybe for a week. Here, the amount of time we have to process packet is very well bounded. It is basically determined by how many stages we have in this pipeline. And then once the packet gets to the very last stage, we have the last, in this case, 3 headers standing. And it goes into a device with an unusual name called deparser, which basically performs the function opposite to what the parsers do. So it takes these headers it gets the body, the payload of the packet, and basically puts them in the right order, forms a new packet, and then sends it out for the processing. So this is the abstract model of how high-speed processing of the packets is performed. There are a couple of things that you need to be aware of. So first of all, it's like a real pipeline or conveyor. If we talk about maybe an automobile plant, so it is a feed-forward architecture. So packets always go, in this case, from left to right. They don't jump. They go through all the stages. And that's what ensures constant processing latency. The resources are typically stage local. That facilitates proper hardware design. Unlike software where, you know, any piece of the program or any process potentially can go to any location in the memory, it is very, very, very difficult to do at high speed. So we tend to keep resources closer to the processing units. In each stage, for example, in Tofino, we have 12 of them, and Tofino 2, we have up to 20. You can perform multiple lookups, and as a result, the programs can be a lot longer than just 20 steps or however many stages we have. And the most interesting thing that every clock, we can process a single packet. So as a result, the performance of the system is very high, and I'll show you in a moment how that works. Before we go to these details, we'll just talk specifically about how match action tables operate. So because they constitute really the essence of the processing. And so if you think about match action tables, these are indeed tables, not very different from, say, Excel spreadsheets. And it is the control plane software that typically populates these tables. One difference is that they don't have like the exact rectangular form. They have one extra entry there, which signifies the default action. And I'll explain what it is in a second. So the data come in from the header and metadata bus. The device can select which specific header fields it wants to use to form a lookup key. And then this lookup key is used to perform a lookup in the table. And so obviously there could be two outcomes fundamentally. Either we will have a hit, and so we find the corresponding entry in the table, and so then we will use this entry that will give us the action and the action data that we want to perform this action with. Or if we have a miss, that's precisely when we use this default action and default action data. And once we have a choice, we make a choice using that little hit signal, which one of those two we're using. The results will go into the execution unit. They can also, the same execution unit has access to other header and metadata fields that are carried on that bus. And the results are placed back onto the same header and metadata bus. And this is a very, very important thing here, because as you could see, the input and the output of a match action table have exact same structures. This is the same bus. So we can string in together many, many tables and many, many stages for as long as we have space in silicon. That's how this works. Now, when we want to build a real device, we need to kind of go a little bit further. Typically, switches today consist of two pipelines, the ingress pipeline and the egress pipeline. That's a very standard practice because switches that, for example, need to support multicast, and that's only possible when you have two pipelines. So in case of Tofino and Tofino native architecture, we have two pipelines which look very, very similar. So both ingress and egress pipeline have all the same components. So they have the parser, ingress and egress parser. We have ingress and egress match action pipeline, and we have ingress and egress deparser. And the other thing that is crucial to operation of any real-world device are the so-called fixed function components. Unfortunately, today we cannot express everything in P4, and so we need some additional components. We need packet ingress and egress components so we can get the data into the switch and out of the switch. And between ingress and egress pipelines, it's another very important fixed function device called packet replication engine. Think of it as a multicast engine, and a traffic manager, which performs packet bufferization, queuing, and scheduling. What is important is that it doesn't really matter what kind of configuration you have in your pipeline. Does it have this configuration, or it can have any kind of other shapes? What type of traffic manager and packet replication engine you can use from P4 standpoint, and we'll talk about the language in a second. They all look the same because we can control these components using the so-called intrinsic metadata, a set of well-defined variables which tell the devices what to do or put in information about what these devices have done for us. So for example, when the packet comes in, the intrinsic metadata can contain information such as ingress port or timestamp, and then output intrinsic metadata can contain a flag, whether we want to drop a packet or we want to send it to a port, and so on and so forth. So if you look at the, this again is a very abstract picture. And the other thing that is also very important, and also P4 language has facilities for that, is that in reality, many devices have specialized components. They're called externs. They can perform unusual computations, like, for example, they can compute hash, or they can produce a random number, or they can do all kinds of things that are necessary to build interesting programs. And again, the language is very flexible. So it allows us to have all kinds of different pipelines with all kinds of different components, but like a Latin alphabet, which we can use to write all kinds of different languages, which might have nothing in common. Same way, P4 language allows us to describe programs which run on different hardware with completely different architectures. If we look at Tofino specifically, you will see that's pretty much how it is. So think of this as a device in its full configuration. It has 4 independent processing pipes. Think of them as like 4 CPU cores. They can all work independently. There is, of course, common logic, so we can connect the chip to the PCIe bus. There are DMA engines and so on and so forth. But ultimately, what happens is packets come in, the ports are hardwired to a particular pipe. So for example, port 0 is wired to pipe 0, and the packet is received and processed in here. And then we have a device called traffic manager, as I mentioned, and that is the place where packets can go from port to port or from pipe to pipe. So this device is the most complicated part of the whole chip because it has to be connected to all 4 pipes. And so it has like 4 times the performance of all the other components. That switches the packets, and then they can be processed at the egress. Overall, of course, things are a lot more complicated. So I kind of prepared a little animation that might be a little bit fun to see how packets go through the real pipeline. So this is a more technical drawing of a real pipeline of such a device. As you can see, packets enter the switch, and every clock, and Tofino operates at 1.22 gigahertz. So each pipe can process 1.22 billion packets per second. A new packet comes in. It is first received, and then after going through some technical buffers, it is parsed. We have actually 18 parsers which work on packets in parallel. Packets received from different ports can be parsed in parallel because parsing is a relatively slow operation. Unlike the match action where we can do a lot of things in parallel, for parsing you need to process packets byte by byte, so to speak. So you need a little bit more time. And then packets get into the heart of the switch, which is the match action pipeline. So in Tofino, we have 12 stages. In Tofino 2, as I said, we have 20. And that's where we perform these match action operations and decide what needs to be done with the packet. After the first pass through this match action pipeline, the packet gets into the ingress deparser. We reconstruct the new packet in the ingress packet constructor, and then it gets stored in the traffic manager, and eventually it gets queued, maybe it gets replicated prior to that. And then as you see, it goes for the next round, which is egress processing. So there it is parsed again, this time by the egress parsers. Then it goes through the match action units again. And so as you could see, it's effectively in case of Tofino, it doesn't have to be that way, but in case of Tofino, these match action units effectively act as a two-threaded device. So they process two packets independently. And then finally, the packet, we reassemble the final packet, reconstruct the full packet byte stream, and send it out to the egress. What might be interesting is for you to notice that even though we process one packet per clock, the pipeline, even on this animation, is pretty long. And so as you can imagine, at the same time, we process in here a couple of dozen packets. In reality, Tofino, a packet can take anywhere from a couple dozen to a couple hundred clocks to pass through the pipelines, which means that each pipe processes up to, I would say, 700 packets in parallel. That's one of the secrets of why these devices are so high performant, is because their pipelines are very, very long. In comparison, for example, a typical CPU pipeline is about 15 clocks. And now, of course, we need to talk about how to program these devices, how to describe data plane algorithms so that we can produce programs that are suitable for these devices. And that's, of course, where we need to talk about P4 language, and specifically P4.16 language. So when we started designing this language, we had a couple of specific goals. We want to build a very specialized language that will facilitate programming of these high-speed pipelines. P4 is not a general purpose language. I do not expect people to, I don't know, write music in P4 or process pictures or do any kinds of fun stuff that we typically use with other languages. It has a fairly limited application just for packet manipulation. We wanted to build a language that will allow us to program any kind of data planes. It doesn't matter what kind of protocol we want to process. So even if you want to process IP or Ethernet or any other standard protocol that you can think, in case of P4, they're all the same. It's a protocol independent language. We also try to build a language to be target independent so that it can express algorithms for a variety of devices. And because it is a programming language, obviously it will give us the field programmability. So you can write a program in P4, load it on the device, it will get its personality. Then you can write another program, load it on the same device, it will get another personality, and so on. And one of the most important things was, and I think that was one of the best decisions we ever made, is that we wanted from the beginning for this language to be a community-driven language. So there is an organization called P4.org. It's a member of Linux Foundation, a part of the ONF project, which has tons and tons of members. The membership is free. Everything is contributed under permissive Apache license. So if you'd like to contribute, and I'll mention that later again, one of the best things you can do is to join P4.org as well. So P4 language and P4, the name P4 stands for Programming Protocol Independent Packet Processors. That name came in 2013. And since then, we actually went through 2 generations of the language, or essentially 2 very different dialects. The older one that we sort of published specification 2014 is called P4.14. And then we worked on the long-term evolution of the language, which is now called P4.16. And this one is being in use for the last 5 years, and we don't see any end in sight. So that's what we are really using. It is still a fairly simple language. It has a couple of basic elements. So there's always the data types, so we can describe what kind of data we process. It has a rich expression system and various operations on the data as usual. Although, for example, some things that are not necessary for switching and can create problems like division are absent in P4, because if you have division, you always have to figure out how to process, say, divide by 0 exceptions, and we don't really want that. There is a way to express parsers, which we program as finite state machines. So it's a fairly unusual way of programming. And we have so-called controls, which look very simple, like pieces of C code, where we execute things sequentially, just same way as you would write in any familiar programming language. And so these controls are used to express both match action processing as well as deparsing. And then P4 has a couple of additional facilities that are typically not used by the ordinary users, but they allow the vendors to express the details of their specific programs. So they allow vendors to express what kind of signals their target is using to control fixed function components or interact with them, and what kind of additional components it has that are available to P4 programs to perform some specialized operations. So here I have some examples of how you can write P4 code. So here, for example, is the code that you can write in P4 to express standard headers like Ethernet or VLAN tag or IPv4 headers. And as you could see, it is a very self-explanatory description. You open any RFC, you will be able to write the headers with the same speed you probably can type. Here is an example of a parser expressed in P4. We start with a state called start. We can extract certain headers, transition to the new state. So here, for example, I transition to the state parse Ethernet, extract the Ethernet header, check the ether type. If the ether type is 8100, TPID ether type, I transition to the next state, parse VLAN tag. Otherwise, I transition to another state called parse IPv4, and so on. So again, a very, very simple set of, but powerful set of constructs allowing us to express our algorithms. Here's how we can define actions. Very simple, very similar to how we do it for writing, for example, functions in any other formal programming language. In this particular case, these actions, one sends the packet to a port, another one drops a packet, manipulate the so-called intrinsic metadata specific to Tefino native architecture. And then you can define a table. You can specify what kind of field you want to match on. In this case, it's IPv4 destination address. How you want to perform the match. In this case, you want to do exact match. What kind of actions are possible in the table. You can specify the size of the table. And so that is how this table sort of can be represented as an abstract picture. Same way you can define another table and use longest prefix match, a very typical match that we use for our IPv4 and IPv6 routing. And so that is a very similar table, just the key is slightly different because even though we use the same field, we use a different match kind. And here's how you can represent algorithms in P4. So you declare the resources like actions and tables, and then it's just a fairly standard piece of code where you can check if IPv4 header is valid. You try to perform a match action in IPv4 host table using exact match. If you have a miss in that table, let's do a match in the other table, which is IPv4 LPM. So this is kind of the basics. And out of these very basics, in fact, the language is not much bigger than this. You can build a lot of cool stuff. That is the most interesting things. And these are just some examples of what people done with Tofino already. So people build caches where they cache DNS addresses. They can build some security appliances, layer 4 load balancers, all kinds of different routers and switches and NAT appliances and whatnot. And again, besides just Tofino family devices, you can find NICs, which can be programmed in P4. You can find software switches and so on. So there's a lot of space for your creativity. As we say in Russian, it's only your creativity which is really the limit. So I hope I gave you a good overview. So now what I would like to do is I would like to conclude a little bit. So first of all, we discussed how these programmable packet processors, and Intel just came up with a new term called intelligent fabric processors, but it's the same. How can they enable really the innovation? And the innovation happens when you can do things at the line rate at the highest speeds possible today, which is what Intel Tofino family devices allow you to do. And of course, they come with P416 language. That's how you can program them. And the other thing that I wanted to mention is a couple of practical steps that you can take to start doing this. And I see a lot of familiar names and faces here, which is really great because I know some people took this step. So first of all, you can join Intel Connectivity Research Program. And second, you can attend Intel Connectivity Academy to learn about the devices. And then, of course, you should be able to get the hardware from a variety of vendors and start innovating. If I have a couple minutes, I wanted to just say a couple words about Intel Connectivity Research Program and Intel Connectivity Academy. So Intel Connectivity Research Program is a program which unites people from all over the world, from academic and research organizations, but not only. Some commercial organizations also join this program so that they can do joint development together with the universities. This is the link, of course, where you can find all the information. The membership is free. It is very simple click-through process how you can apply. Unfortunately, we still have a bunch of stuff under NDA, and so one of the major reasons you want to apply is so that you can get access to all the materials which are under NDA, including the software. And there are other benefits, of course, to that. So we run a very good online support forum where people ask questions and community members help them. We provide generous discounts for training. Many vendors provide discounts for equipment and the software. And also we provide free editorial service for the papers. And this is the link. If you will later on get the presentation, we publish the link to the papers. We kind of collect them, the papers that the ICRP members write and publish. This is the map of where we have the members, as you could see, all over the world, and it's more than 250 organizations today. If you think that we don't have enough of these pinpoints, if you do zoom a little bit, just in Montreal, we have 3 universities, so that's why we don't have a lot of these pinpoints because just the scale is not very high. And the other thing that I would encourage you to do, and in fact, it's also one of the requirements for membership in Intel Connectivity Research Program, is attending Intel Connectivity Academy. I'm very happy to see some of my current and my former students here. It's a great way to learn about P4 and Tofino. It's not only lectures, but they're hands-on labs. And we run those hands-on labs on AWS VMs, so they are located as close to where you are as possible. So it doesn't matter if you're in South Africa or in Brazil or in Australia, we run a VM nearby. There are lots of exercises to do, and members of Intel Connectivity Research Program get academic discounts to attend Intel Connectivity Academy. And that's pretty much all I have for today. So I guess the rest I will leave for questions and answers. Thank you very much.
Thank you very much, Vladimir. If you have any question, please feel free to write in the chat window or unmute yourself.
And I see there's might be something. So question from Zaji, is there a forum with already written up scripts? I wouldn't say a forum with the already written up scripts, but there are definitely a lot of code. I didn't mention that, but we opened the Tofino native architecture and our interfaces to the public. And so now most of the researchers which write code for Tofino do publish their code on GitHub, and there you can find a lot of very interesting code, and it sometimes comes with the scripts as well. Question from Tim Reiner. That's a very involved question. Some vendor devices have P4 runtime. How is that similar, different to Tofino? So Tim, what P4 runtime is, let me just go back to one of my slides. It is an API which is necessary, or it is one of the APIs that is used by the control plane to interface with the data plane, because as you see in P4 programs, which is declare the tables, but the actual contents, the actual entries in the tables need to be populated through some API. And so we call those data plane APIs. They come in a variety of forms of fashions. So initially, the community decided to settle on a API called P4 runtime. That's a kind of second generation of the API. This API, unfortunately, has a bunch of issues that makes it not very suitable for practical purposes. And so what we do instead of Barefoot, we use a different set of APIs called Barefoot Runtime Interface. Well, at Intel now, Barefoot Runtime Interface, although now I think we are working on the new version of this, which will be less specific to Barefoot. There are some technical differences between different APIs. So in case of P4 runtime, think of this as an object-oriented API. So you have a variety of objects. For example, table is an object, counters are an object, meters are an object, and so on. And each object has certain methods. So you can add an entry to a table, or you can read a counter, that sort of thing. In case of Barefoot Runtime Interface, it is a different API that we use with Tofino. We can use P4 runtime, but the problem is that P4 runtime does not have objects which are specific to Tofino. And even though that allows us to add extensions, that will pretty much make our P4 runtime code not very useful to anyone who is not familiar with those extensions. And also, it is somewhat difficult for the compiler to generate the code for any objects which it is not familiar with. So we use a slightly different API called Barefoot Runtime Interface, where everything is expressed as a table. So the table becomes the root object of the API. And then whether you want to add an entry to a table, or you want to set a new value for the counter, or you want to, for example, access a register, or you want to access a multicast group, you will use exactly the same interface. You'll just manipulating a table, and all you need to know is which specific columns this table has. Come into our Intel Connectivity Academy, and I'll tell you a lot more about these APIs.
Thank you. Is there any other questions? Vladimir, I have one question. These devices are very parallel, a lot of parallelism. May you comment about that? How is the performance so much greater than a regular CPU, the dimension of parallelism?
Well, so absolutely. So one thing I mentioned, right, is that the length of the pipeline is much higher than the length of a typical CPU. So if you look at the Intel CPU, the typical pipeline length is somewhere between 12 and 15, maybe 17 clocks. Here we're talking about 500, 700 or even more clocks. So that's a huge difference in parallelism. So if you think about one pipe in Tofino, it processes 700 packets at the same time, and with 4 pipes, that's 2,800 packets. That's one way to see the difference in parallelism. The other way, if you think about that, the header and metadata bus, which which connects the individual stages, like for example here. So, Intel CPUs, for example, they're 64-bit CPUs. The width of this bus in Tofino 1 is 4 kilobits. So you can think of Tofino as a 4 kilobit device, which again is very different performance-wise, of course. And every clock, when we go through these match action stages and we look at these execution units, they can actually perform more than 200 operations in one clock. So that's what pretty much ensures that high performance of Tofino that is very, very different in terms of what would have happened if we tried to process these packets using regular CPUs. Of course, we have other components. For example, if we want to do LPM, longest prefix match, or if we want to do ternary match, we use TCAMs, something that is not commonly available in CPUs, and so on and so forth.
Thank you. Any questions? Any other questions? Okay, there is no more questions. So I will be posting information, a slide for those who want to join Intel Connectivity Academy. So all the information will be in our website. So thank you very much, Vladimir.
Thank you. Bye-bye.
We will have a break. It's 2:56. We will be back at 3:10, and we will have our first hands-on session. We will have an introduction to P4 and BMv2 and how to write, compile, and download P4 code to a software switch, BMv2. So we will come back again at 3:10 p.m. Eastern time. All right, welcome back. We will start our first hand-on session, Intro to P4 and BMv2. I want to mention that the PowerPoint slides in two formats, PDF and PowerPoint, are available. And there is some links. If you didn't register yet, we will be using a virtual platform. So in slide number 14, there is an URL to register to the platform. This is the same URL that was sent last week. If you did register, you can reserve time and you will have the pod deploy when I mentioned that before we start. So this slide again are already online. Hands-on session number 1. So this hands-on session is about an intro to P4 and BMv2. And before we start, I wanna mention again that we are gonna be using BMv2. This is a software switch that is open source, typically used for teaching, researching ideas, good to validate new ideas, research ideas. This lab library contains 8 labs. We will just do 2 here. From an intro to Mininet, we will be using Mininet. The BMv2 switch will be integrated to Mininet. Then an intro to P4, BMv2, all the way to lab 6, 7, populating, managing match action tables, and packet parsing. So these lab experiments include step-by-step directions. So the idea, as we said at the very beginning, is that these lab libraries are used for associate, bachelor, all the way to grad level. And then there are some challenges, exercises. They don't have directions, but they are also included in the virtual machine. Before I continue, I want to mention also, I think I forgot, in our website, there is a table, resources. We're using one virtual machine, and if you wish to download this virtual machine and run on your own computer, the link to download is here in the website. For those who are not that familiar with Mininet, Mininet is a virtual testbed that contains nodes. Nodes are containers, or more specifically, they are network namespaces. It's pretty good for fast prototyping of new protocols, new ideas. Very simple to test complex topologies. It is quite realistic in the sense that it runs real code. There are BMv2. There are also hosts running Linux. Is open source, and it can run pretty large networks. We integrated Mininet with MiniEdit, which is a graphical user interface that is also linked with Mininet. Here we have an example. On the left-hand side, we have a network with 2 hosts, H1 and H2, and 1 switch, S1. On the right-hand side is the topology that we're building using MiniEdit. The panel includes several devices, for example, host devices. Let's see if we have a better example. Right here, host devices, P4 switches, SDN switches, legacy switches, routers. These are traditional routers. We use FR routing. Linux devices, I already mentioned. So it's a very rich platform. Pretty easy to manipulate the devices using the graphical user interface. Easy to, for example, assign IPv4, IPv6 addresses. Easy to test very quickly. again, using the graphical user interface with a simple right click, opening a terminal, or even manipulating the switch that we will see in the labs. We build examples using BMv2, and they are running inside Docker containers. The code is written in Visual Studio Code with a built-in terminal. On the left-hand side here, we have an example, a topology. On the right-hand side, we have a code that is going to be deployed on one of the BMv2 switches. And then at the bottom here, we have the built-in terminal. So all the environment is available right away. As I mentioned before, there are some other devices available: FR routers, OVS switches, Linux host. And this is the workflow that we will use. First, we have a P4 program, .p4. In this example, is basic.p4. Then there is an architecture module. We will be using the V1 model. And this is what we would replace if we were using, for example, Tofino switches. We will use the Tofino native architecture here, TNA. We have the compiler, and the compiler generating the executable file that is going to be loaded into the data plane of the switch. The switch, the control plane interacts with the data plane using a simple switch command line interface. So that's the environment. The first lab that we will be doing here is about P4 program building blocks. We will be looking at the different building blocks as Vladimir was discussing before. And in order to do so, I want to let Eli lead to that exercise. I want to briefly introduce Eli. Eli is a PhD student here in the College of Engineering and Computing. He's working with me, has been working with me for the last 3 years. His research focused on P4 programmable switches, network security, blockchain, IoT, software-defined networking. Some examples: he has been working here at USC, dynamic router buffering, conversational media traffic offloading to the data plane, botnet detections in the data plane, and a few other projects. I want to give credit Eli also because he is one of the individuals who developed these labs. So Eli, are you there? Can you share your screen right now?
Yes, sure. Thank you, Doctor. All right. So hello, everyone. So I will go over the slides, and then we will shift to the practical part, the hands-on part. So before we do that, I will also describe what architecture we'll be using. So Vladimir was mentioning the PISA, which is the general architecture. But in our case, we're going to be use an instance of this PISA, which is called V1 model. And the V1 model, first, can you see my screen?
Eli, yes, we can see your screen.
Okay.
Share this screen.
Okay, sorry for that. I was trying to share the right screen. I'm using two screens here. So basically, we will be working with the V1 model, and V1 model is a P416 architecture that is used with the software switch BMv2. And the BMv2 has a target, and this is basically the actual switch, and it has the daemon and all the executables there. It's called the simple switch. And we can see here at the bottom, this is a diagram showing the main components of the V1 model architecture. So first we have a programmable parser. Then we have an ingress match action pipeline where we have multiple stages. Then we have a traffic manager. This is the configurable component. This is not programmable. Then we have the egress pipeline. And finally, we have a programmable deparser. So all these components are programmable. Only the traffic manager is not. What we will be doing in this lab, we will go over an already written program. So we will see the different files and how they are mapped to these components. And then we will see how we can compile and then run that program on the software switch. So what we decided to do in the lab series, we decided to basically split the program, the whole P4 program, into separate files. And each file will have whatever that component is doing. So for instance, we will have a dedicated file called parser.p4. This is where we're going to be implementing all the parsing capability of the P4 switch. Then we have another file called ingress.p4. This is where we're going to be having all the tables and all the match action pipeline related to the ingress. Same thing for the egress and for the deparser, and also for the checksum verification. So I will go again over these slides. This is just the instruction to access the platform. So if you did not register yet to the platform, and this is what was sent through email, you can do so now. So there's this link. Jose, if you can please copy it to the chat. And basically you just go there, you have to fill a form, and then you're gonna receive a verification key to your email. Once you're there, you're gonna complete the enrollment, accept the terms and condition. And then once you are at that point, you'll be able to claim free access and then start by using the platform. Now, if you already registered before, all you have to do is just log in, okay? And this is the link for logging in here. When you log in there, you will see that there's a course called Programmable Switches Workshop. You just have to select the lab that you would like to do, and then the reservation will start and you will be able to start doing that lab. So in our case, we will be doing lab number 3. For this lab, we have a very simple topology. We have one P4 switch and we have 2 hosts, H1 and H2. And we will see how we can compile the program, the P4 program, and then push the output of this compiler to be used as a program for the switch, right? As the data plane description. And then we will see how we can start the daemon, allocate the interfaces, and perform a simple test to verify that this program is running. Okay, so now I will shift to the platform where we're going to start by doing the exercise. So as you can see here, I'm inside this platform. So that's the NDG platform. And here we have a course called Programmable Switches Workshop. We have to click on that. And here is where you're gonna see all the different labs and exercises. Okay. All we have to do now is just select which lab we're interested in. We're gonna go over lab number 3.
Also, while you are doing this, Ali, I want to remind that we put online the virtual machine that we're using. So the virtual machine is available in the website.
You can find it under the resources table. That's the first link here. it's taking some time. I will try to redo that.
Robert, is my assumption correct that you might either use the VM or the NDG platform to complete all the labs? That's correct. So you can download the virtual machine and do the labs in the virtual machine. Typically, I know I'm trying to figure out why it's taking so long to get the virtual machine. Typically, it's happening in few seconds. And also, Robert, the lab manuals are online. Eli, do you want to show where the lab manuals are in case that somebody want to just download the virtual machine?
Yeah, certainly. So in our website, if you go to the top, there is a page called Cyber Training. So you can go there and basically you'll find all these labs. There's a one single PDF file that contains everything here. So if you click here, you will find all these different labs and their exercises, and you're gonna be able to go over them if you decide to have your own machine running locally, and if you don't wanna use the platform. I think now this is ready. So this is what looks like whenever you do the reservation for a given lab. You will see a pod. In our lab here, we only have one device. This is the client. And within that client, we'll be starting Mininet and creating the whole environment where we have a switch and hosts and basically do the whole lab. Now, what we have to do is, you can see here also there's a button called content. This is where we can see the actual content of the lab. So you can open it in a new window. And I typically like to put them aside so that basically we can see the content and at the same time we can go over the lab. So on the left-hand side here now you can see this is the lab content. So first we have a table of content. In all the labs you will see a short overview. What are the objectives of the lab? And there's a table that contains the credentials. So for instance, sometimes you might run a command with higher privilege, you would need the password. So you would see it here, which is a password all caps. And then we have the roadmap. We start first by describing the theory behind the topic. For instance, here we are talking about the PISA architecture. And then we keep continuing with all the theory that we will plan to go over through the hands-on part later on in this lab. So all of this is what we were talking about in the slides. And actually in section 2, this is where the actual hands-on start. Okay. So now I will start by going to the client. So you can click on client. And from there, we will start by following the steps here step by step. So the first step, step number 1, we have a shortcut to Mini-Edit, the program that it's a graphical user interface for Mininet, and it's on the desktop. So all we have to do is launch that program. And now we are asked for a password. The password is password, all small caps. And now we can see that Mini-Edit is running. We can start by deploying some switches, some devices. But what we're going to be doing, we're going to be using the topologies that we already created for each lab. So each lab will have its own topology file. And since we are doing now lab number 3, we'll start by opening this lab. So file, open, I'm going here in step number 2, and then lab 3, and we have lab3.mn. This is the topology file in Mininet. And we can see now that it's showing our topology, which consists of a P4 switch and 2 end hosts. The next step is to start the emulation, start all the devices here, and we do so by clicking on the run button. So whenever you click on run, those buttons here should be grayed out. It means that now the topology has started, the emulation has started. We can actually start now using those devices. So in step number 2.1, we're gonna now see how we can execute a command on a certain host. So in this case, we will open the terminal of host H1 and perform a simple connectivity test using ping. So to issue a command on a certain host, in this case H1, we right-click on the host and we hold the right click, and then we select terminal. And this is going to open for us a terminal, which is a Linux-based terminal. So all the commands that you would typically type in Linux can be executed here. You can use ifconfig to see the interface. You can use ping, any kind of command that you are interested in. One thing I have to mention as well is that the IP addresses are already configured within the topology. So host H1 has the IP address 10.0.0.1, and H2 has 10.0.0.2. And now what we're trying to do in step number 2 here is send some ping from host H1 to host H2. So I will start by typing this command, ping 10.0.0.2 -c 4. It means that I want to send 4 packets, 4 ping packets. And what we can see here is that there is no connectivity, which is expected in this case. And the reason is our P4 program is not deployed yet. There's nothing on the switch that will start doing the actual packet forwarding. And that's why simply we are dropping all these packets. Okay. Now in section number 3, we will iterate over the components of the basic P4 program, and we will see also the whole development environment. We will start first by launching a terminal by clicking on the icon on the desktop. So we can minimize those, or we can click on this show desktop button here so that we minimize everything. And then we double click on terminal. So we are now doing this step here. Then I will type this command, code. Code is the program that we will use to modify the P4 program. And I will pass as parameter to this command the lab name, the location of the files where this lab will be, or the ones that this lab will be using, right? In our case, this is lab number 3. And once we do that, we will have the Visual Studio Code open. And I just want to describe very briefly here, what do we have once we launch the Visual Studio Code? We can see on the left-hand side, we have the file explorer. So basically all the P4 files, the topology, everything related to that lab, you would find it here. Now currently we are seeing basic.p4, that's our main file, and we'll be invoking other files as well. This is where we describe other components in the architecture. Here on the right, we have the editor. So this is where we're gonna write the program, modify the program. And on the bottom, we have a regular Linux terminal. And the reason we decide to use this kind of styling or the appearance of Visual Studio is because we will be modifying potentially a few files here within the same program. And once we do that, we want to, let's say, compile to test if everything is working well. So we can use this terminal here at the bottom to actually perform the compilation. Okay. Now looking at the first file that we opened here, basic.p4, we can see that we have some include statements. The first two are related to the P4 language. So this is the core.p4. And the second one is related to the architecture definition. In our case here, it's V1 model. So if you are working with Tofino, this is going to be different, might be TNA or something else. And other than that, we have some include statements. These are including the files that we created here. You can see here that we have the double quotes, pretty much similar to what we do in C, right? If you are using the user-defined files, we can include them and use double quotes. So in other words, this basic file now is including all these files that we will potentially use when describe our program. Next, I will go and look at what is the headers.p4 file look like. So we have a file called headers.p4. I will click on that. And what we can see here is we have a few things to notice. First, we have some constant definitions. So I'm telling here that type IPv4 is equal to 800. This is just a constant. You can define that here. We are also inserting some type defs. This is just to make the program more readable. So instead of saying that I want a field to be equal to 48 bits, I can write MAC address underscore T, right? So this is going to be used when defining these fields. And then I will start by listing all the headers that I'm interested in parsing and using in my P4 program. So for example, we are first starting with the Ethernet header. So we start by typing header Ethernet, and we describe here what are the fields that are inside the Ethernet header. Okay, so this information you can get it from basically RFCs, or a simple Google search for any of these standardized protocol will give you all the fields and how big each field inside the header, right? So here, because we defined the MAC address to be bit 48, it's as if we are saying bit 48 destination address and bit 48 source address. Now the ether type, which is a field that will allow us to determine what is the type of the next header, this is only 16 bits, so we define bit 16 and ether type. And we do the same thing for IPv4. So I'm sure many of you are already familiar with these fields. Specifically here we have the source address, destination address. These are for IPv4 as well. And you have other fields, for example, the TTL, the protocol, and so on. Also, Vladimir was mentioning that there is some metadata bus that will be traveling through this pipeline, and this is where you can copy some information from throughout this pipeline. And here we have it, but we kept it empty just for simplicity. We're not going to use metadata. And finally, we are combining these headers into a single struct, which we are calling headers. So we're saying that my headers will potentially be Ethernet and IPv4. Now, the next step is to look at the parser. So we have a file called parser.p4. And this is where actually we are defining how to parse packets that are coming to our P4 program. So the parser includes the headers because definitely we're going to be using Ethernet and IPv4 here. But basically what we can see here is that we just created a parser. We called it my parser. Okay, and this parser accepts some inputs. For example, we have the packet, the header, the metadata, and the standard metadata. And the parser, you can think of it as a state machine. So it has some states, and we will transition from one state to another. And this is how you define how you are doing the actual parsing. The parsers have some standard states. So there's one called start, and this is where the actual starting begins. Okay, so we have start. We are transitioning to another state called parse Ethernet unconditionally. So we are saying, as soon as we start here, just go to parse Ethernet, which we are defining here. Now in parse Ethernet, what we need to do is we need to extract the Ethernet header. And this is what we are doing in this line. So packet.extract header.ethernet. And then we are checking the ether type field in the header. If it is equal to the value of the IPv4, Then, so we are checking this here. Then we go to a state called parse IPv4. Okay, and the default, so in case it's not equal to this value, we'll just accept and then move to the next block in our pipeline. Now going to parse IPv4, this is where we're gonna extract the IPv4 header and then accept so that we go further the pipeline. We have another file, ingress. This is where the control block for the ingress pipeline exists. So we can see here we have some information. I will not go over these because there are other labs that are specific for this purpose. But I just want to mention that the name that we use here for defining this control, we will be using it later on whenever we start the whole pipeline. Okay, so in this case, this is my ingress. For the parser, we used my parser and so on. Next, we have an egress file for the egress pipeline. Here it's empty. We don't have anything in the egress pipeline, and we called it my egress. So we are in this step now. Then we have a checksum file. Also, we can see that we have two actual checksum here. First is the verify checksum, and then the compute checksum. Okay, and also these will be used later on whenever we start the pipeline. Now, finally, we have a file for the deparser, and that's the last component in our pipeline. This is where you specify which headers you want to emit. We call it here my deparser. Now, all these files that I showed you, basically, this can be considered like a template. So in most P4 programs, you would have very, very similar structure. And it's about what you write inside these controls and these parsers is what make your program different than the others, right? So you don't need, obviously, like to memorize all this stuff. This is like a template, a skeleton program. You can use it and then start adding on top of it. Now, going back to the basic.p4, because this is our main program, this is our starting point, right? I click on basic.p4, so we are in step number 1. And now the second part is to actually insert some piece of code that will actually start a new instance of this switch, right, of this V1 switch. And we will insert it below the comment here, okay? I will type the text that you see here, the code that you see here. So V1 switch. And then inside it, you can see here that we are defining them sequentially as they are defined in the pipeline. So we start with the parser, which we called my parser. And then we have my verify checksum. This is basically if you want to verify some checksum for the packet, if you want to drop it so that, you know, if it has some invalid checksum, you are doing it at the beginning. Then we have the ingress block, which we called it my ingress. And then we have the egress, which we called it my egress. And then we have my compute checksum. And this is where we actually update the checksum because you know that before programs most probably will do some header modification and you want to make sure to recompute the checksum so that your packet remains valid. And finally, we have the deparser, which we called it my deparser. Okay, and we give it a name here, main. So basically you can consider this as the main function in a certain C program that will start invoking other functions as well. Okay, now once we write this piece of code here, it means that our basic will actually use whatever we included in those files to start an instance of our P1 switch. Now, once we finish writing, it's very important to save the file, right? And in Visual Studio Code, you can see here that's showing this black circle. We want to make sure we save it. You can use Control S or File Save. Once it's saved, it should disappear. This means that your program is saved. Now going to step number 4, we're going to start by compiling the program and loading it to our switch. So the compiler that we use is the P4C. This is the reference compiler. This is a standard compiler, very well known in the community. So all we have to do is just type in P4C and the program name, which is basic.p4. And once we execute that, if we had some syntax error, they should appear here in the terminal. Otherwise, your compilation was successful, and you will see that some new files were generated here, specifically these two files, basic.json and basic.p4i. What we care about at this point is only the basic.json, because this is the file that really describes what the data plane is doing. So this is the file that will be used by the BMv2 switch to describe the data plane. This is, if you are using, for example, other architectures, it might be a binary file, or it might be any kind of file that will be accepted by that target switch. For this software switch, BMv2, it's a JSON file, and it's called here basic.json. Usually it depends on what name you provide for your main P4 file. And this is going to be used as a prefix for the output, and the file type is a JSON file. So now we did the compilation, we have this output, but it's still on our local device. The next thing we have to do is we need to push it to our switch S1, which we started in Mininet. And we already provided a script. This is a very simple script that is just copying this file to the file system of the Docker container, which is running the software switch BMv2. So push to switch basic.json, and then the switch name. This way, if you have multiple switches, you can push them to multiple switches, or you can push different programs to different switches. So it's asking us for a password. Again, the password is password, all small caps. Okay. Now we will verify that our file is now in the switch, and we will see how we can start the switch with that file. So we will go back to mini edit. We will maximize it from here. And to be able to go inside our switch, we will do the same thing as we did with the host. Right click on the switch and then click on terminal. Now we are inside the terminal of the software switch. Here, this is actually like a software switch that is running on a Ubuntu Linux. So same thing, we can issue any kind of command here, basically. And we can use ls to verify that our file that we pushed, the basic.json, is now inside the file system of our switch. Okay. Now that we know that our file is there, we need to start configuring the switch and give it this file as input. But before we do so, we want to make sure to allocate the interfaces to that switch. We are probably all familiar with the ifconfig command, which allows us to see the interfaces on Linux. So I typed in here ifconfig, and you can see that we have a few interfaces, one for management, a loopback interface. And also we have S1-ETH0 and S1-ETH1. And basically those are the interfaces that will be used by the software switch. Now, at this point, we will start our switch and allocate the interfaces. Okay, so now I'm in step 2. If we look at this figure here, 28, what we are doing basically is telling, whenever we start the switch, that I want S1-ETH0, this interface here, to have the port number 0 on my switch, and the S1-ETH1 to have the port number 1 on my switch. Okay, and we can specify that once we start the switch, as we are doing here. So to start the switch, we simply write simple_switch. This is the target of BMv2. -I for interface, 0 at S1-ETH0. It means that port 0 is now S1-ETH0. And then -I 1 at S1-ETH1. Now, obviously, you can allocate any kind of interfaces for that switch. Depends on the topology that you are trying to do. Now, another parameter that we are passing is this nanolog IPC and some file location here. And the idea of doing that is that because we want the switch to enable logging. So our goal is to see what is happening inside the switch. We want to see the packet as it traverses through the architecture, our V1 model architecture. So to do so, we instruct the switch to start this logging by using -- nanolog, and we give it the file. Basically, this is working over IPC, inter-process communication. So you give it the location of the file, tmp bm-log.ipc. And now the most important here is to specify our compiled data plane, which is basic.json, right? This is what we pushed from the Visual Studio. And finally, we use AND here just so that we run it on the background. We run it as a background process. Okay. And I will hit enter here. You can see that it told me that we allocated these interfaces as port 0 and port 1. Next, we will load some rules to the switch, and those rules are from the control plane, right? We didn't see them yet. We didn't see how they are, but basically you would need to populate the tables, as Vladimir was saying in his presentation. And this is done through the control plane. So we want to make sure that the tables that we have in our program are populated. For now, we were just going to use a script, but there's a lab later on that will describe exactly how we can populate them with values that we want to insert in our switch. So first, I would press enter here. So this is step number 1, to go back to the terminal. And then I will populate the tables by using simple switch CLI. I pass to it some file that contain all the rules, and it's located in lab3 directory. It's called rules.cmd. Basically, you would have a different directory for each of those labs. We hit the enter, and we can see that some entries were added to the tables. We're not going to discuss them now. We will discuss them later on, but just we need to understand that now the tables are there, are populated. Next, we will start the program. This is the nano message client that will allow us to connect to the switch to see what is happening there, to see the logs that are generated by the switch. All we have to do is just type in nano message client.py. And this is gonna connect to the switch. It obtained this configuration file. And now all the packets that arrive to the switch will be able to troubleshoot how they are passing through our switch, through the pipeline. We can see them here. Next, step number 2 here, we will start a receive program on host H2, because what we are planning to do is to send a packet from H1 to H2. So we can start, this is a simple Python program that just uses Scapy to print some information about a packet that is received. And it uses, sniffing on the interface that a certain device has, right? So if I want to open it on host H2 terminal, this is step number 2. I will right click on H2 to open its terminal, and then just execute receive. And you can see that now it is sniffing packets on the port or on the interface H2-ETH0 in host H2. Next, I will send a packet from host H1. So this is step number 3. I will go back to H1, which you already have it open here. And we will use a script called send.py, also a Python script. It accepts as input. The first parameter is the IP address, destination IP address, and some payload that you want to add on top of your packets. So let's say hello world. And we hit enter. So what we can see here is the output of Scapy, just telling us how the packet looks like. It has an Ethernet header, followed by an IP header, and has also TCP. And at the end, we have some raw payload, which is hello world, that we pass through the command line. Now, we can see here on H2 the same packet arrived. It means that the switch is doing the forwarding. But now, most importantly, let us inspect the terminal of the switch to see what happens there. So I will go back to the terminal of the switch. This is the behavioral model here. Okay, and what we can see here is this is where it starts. So we have a packet in, a packet was received. It was received on port 0. Remember, this 0 is the one that we used when we started the switch, right? From S1 to H0. Then the parser started, right? It performed extraction on the Ethernet header and extraction on the IPv4 header. Okay, then the parser finished execution. And then now we have the pipeline start, which is our ingress pipeline. There we have some tables, which it didn't show, but there is a table that was hit and some actions were executed. Then the pipeline here ended, the ingress pipeline. After that, we have the egress pipeline. But as we've seen, the egress pipeline is empty, so it just started and finished. We didn't have anything inside that pipeline. And then we have the parser. So the parser started. There was some checksum update executed. And then we start by emitting the headers that we are interested in. If you remember, when we checked the MIDI parser, we had the emit Ethernet and emit IPv4. So it's showing us exactly here what headers it emitted. Then the parser finished execution and the packet was sent out of port 1 so that it's forwarded to the host H2. So this is a very important thing to have whenever you write the program, because potentially before program can get complicated. And because they enable those in-network application, the goal is not only just to forward, you might want to do more complex stuff. And logging is a key feature to understand where is your packet currently in this pipeline. Is this table hit? Maybe you would think that why is this condition not being executed? But here you will actually see that there was hit or there was miss, or which kind of pass a certain packet took inside the control block, and so on and so forth. So it's important to have these available so that you can troubleshoot better your program. And this basically concludes lab number 3. So in summary, we just saw the development environment. We saw how we can compile, push the output of the compiler to our switch, start the switch daemon, allocate the interfaces, send a packet, verify that it's received on the other end, and see that all the different components in the architecture were executed as we defined them in our main program. Dr. Jorge, shall we have questions now, or?
Yeah, let's see if there is any question. Thank you, Ali, for the presentation.
Yep.
Well, we wait in case there is any. Ali, do you want to mention the importance of logging, looking at how the packet traverses across the pipeline? We're using BMv2, but in a Tofino environment, this is also available. Do you want to talk about that and how important it is for the deployment of real protocols?
Yeah, certainly. So basically, when you work with hardware, there's a lot of the hardware process a large amount of packets, and it has very high rates. So the logging will not be available as you have it, for example, in the software implementation. And that's why for Tofino, you have two variations. You have the hardware. This is the ASIC. This is the actual switch. And you have the software version of it, which is called Tofino model. Now, in Tofino model, because it's a software switch, it's not designed to be used as a production grade switch. It offers all these kinds of logging. So if you are writing a program that you want to deploy on your hardware, you are still able to see what happens inside the switch when you run it on a Tofino model. Okay, and there's another point that I want to highlight here in this lab. The software switch that we are using, BMv2, is not production grade, which means that you can use it for simple tests like this, experimenting, learning the language, trying new applications. but you cannot make it run at, let's say, 40 gigabits per second. You cannot run it at high rates. I believe the best we could achieve with BMv2, based on what we tried before, was up to 1 gigabits. But that was like the best case scenario. And if you would like to get to that level, you would need also to disable logging. Not only by not providing this parameter that we saw here when we started the switch, but you have to recompile BMv2, and there's some flag that will tell it that I don't want logging at all to be enabled. And this is very, very important if you want to get higher speeds. Otherwise, you're gonna get very, very low packet processing rate. And again, this debugging will allow you to make sure that your program is running well. Later on, you might want to perform some more tests, because those programs will be used in production networks, and you need to make sure that it's working well. And there's ways to test the program. There's the framework PTF. This is like a unit testing framework, packet test framework, specifically for P4. It can be used for BMv2 and Tofino, right? But this is very important, and you don't want to have a program that's kind of working or a little bit buggy to deploy it on a network, because that can have a lot of problems later on.
Thank you. And Eli, there is a question. I will read. What is the purpose of the command line command again? Is it necessary in the exercise, or will it be discussed later? I believe this is referring to the control plane command line interface. I think you have a slide on that, your presentation.
Yeah, so let me check here. So basically the CLI, simple switch CLI, this is just a command that you would use to insert entries inside your tables and to manipulate data plane objects in general. Now, if you want to perform switching or you want to do forwarding, you want to make sure that the tables that you have, let's say you have a table that will match on the destination IP and forward the packet from device A to device B. You want to make sure that it has the information there. It has what we call the rule that will tell it, if you receive a packet that's sent to this specific destination IP, use this output port, right? So you need to insert those. Those happen from the control plane, right? And basically, we are here in this lab specifically, we are just pushing two rules, very simple ones, saying that if a packet comes from port 0, forward it to port 1, and if it comes from port 1, send it out of port 0, right? But if you don't add those, then you won't be able to, if you have a table in your program, you won't be able to do some matching on that table to forward the packet.
Thank you, Eli. There's also other questions. I see the type of arguments in the parser or the parser, in, out. What is the difference?
Yeah, so those are what they call the directions. And basically, there are some things that you can't modify. This you would use them more in when you manipulate, for example, registers. You can decide whether you want to register, whether you want to modify it or not. But basically, in out means that it's going to be used to be read and modified at the same time. And in, it means you are only reading, you're not modifying it. And out means that you might be modifying it as well.
There is a second question, is we include the header field. However, how did we use the extracted values?
That's a great question. In this specific lab, the goal was just to show the whole program. Typically, when you want to parse a certain header, right? Let's say you are parsing IPv4. The goal is to use the fields of the IPv4 header later on in your program, right? But in our case here, we did not use it. But if you are, let's say you want to decrement the TTL or you want to modify something in the IPv4, you need to parse it. The goal was just to show you how the parser looks like and how you can go from one state to another one. But eventually, if you would like to use a certain header, you would need to parse it.
Thank you, Lee. I don't see any other questions. So what we will do is, right now it's 4:05. We will have a 5-minute break, and then we will have our second hands-on session. We will start at 4:10 p.m. Eastern time. So we will have a break right now. Right, so let's continue with our program. So the last session of today is the second hands-on session. Eli will be leading this session. He's going to be talking about parser implementation, writing a parser for IPv4 and IPv6. Eli, are you ready?
Yes.
So I will let you share the screen.
Okay, so now in the second part of the hands-on, we will see how we can implement the parser. We will be writing a parser for IPv4 and for IPv6. So going back to the original figure that shows the pipeline, we are now working in the first element here, which is the programmable parser. Now, it's a programmable parser. This means that allows you to parse arbitrary headers, and it has a finite state machine. What we need to understand here is that we don't have to we don't have to parse standardized protocols such as IPv4 or Ethernet. We can basically create our own protocols, and because of this programmability of the parser, we can actually parse those protocols. Okay, and this is expressed in a state machine, as we can see here. So we start with a given state, let's say the start state, and then we jump from one state to another. And this jumping here, we call it transition. So how can we define those? We've seen them briefly in our program. Now we will write them again and compile the program and test everything. But the idea here is that a certain protocol has some headers. For example, here we can see we have the IPv4 header. This is how it looks like. So here you have the bit numbers from 0 to 31, and then you have these different fields. So what you typically do is you would define a new header by using the header keyword, and then you give it the name. Here it's IPv4. We add to it _t because we'll be using it as a type to instantiate a new header. And basically, you would start mapping all these fields to their actual representation here in P4. So for example, version starts from bit 0 to 3. So these are 4 bits. So bit 4 version. You have IHL, another 4 bits. So bit 4 IHL. Now, if we look here at this now, we can see that these two fields, the SCP and DCN, can be used for this diff serve. So you have the option to say, I want to make it, let's say, bit 6 DSCP and then bit 2 ECN. Let's say if you are planning to use those separately, you have the option to do so, or you can actually combine them, right? And typically, whatever you parse here, you have the intention of using it later on in your program. And then you have fields such as the total length, identifier, and so on. And then at the end, you have here the source IP, destination IP. Okay, so you can see them here, source IP, destination IP. Now, the IP options, they are optional. They're not included here, but also you have the option to actually parse these options. So how can we write this parser? We have to always start by the starting state, and it's called start. So you define that. You transition from one state to another by using the transition keyword. And then basically you would decide which state you want to go to next based on some fields that you have in the current header. Okay. In this case, we are saying let's look at the ether type value. If it is equal to IPv4, then we go to the parse IPv4 state. Otherwise, we can reject. So the objective of this lab, we will use the exact same topology as the one that we used before. We have one P4 switch and two end hosts. What we will be doing is defining the headers for the Ethernet, the IPv4, and the IPv6. Then we will implement the parser. And later on, when we send the packet, we will be verifying that based on whatever is inside that header, right? If it is IPv4, then the IPv4 state will be executed. If it is IPv6, then the IPv6 state will be executed. Here I added at the end a reference on how these headers look like. So basically, this is what we will be defining in our headers file. All right, so let's move now to the hands-on part. So I already made the reservation. Now we are working on lab number 4, which is called parser implementation. Okay. I will do the same thing. I will undock it, put it aside, and then have the client on the right-hand side. Okay. So as usual, we have few description on what's the lab about, like in the previous lab that we discussed. Now here, because we are talking about the parser, you will see in the intro, we are telling the reader what these headers look like, the Ethernet, the IPv4, and the IPv6. Okay, but again, if you are planning to parse some other kind of header, all you have to do is look at what are the fields that are inside that header. And based on those fields, you will start by writing the header description in your P4 program. Okay, and here we are showing a snippet of this P4 program that has these headers there. And then we go to the programmable parser part and we describe the syntax. But I will not go over them here. We will go over them as we do the lab. So we'll start with the hands-on part in section number 2. So again, we have the same topology. We can see here now that beside the 10.001 and 10.002 IP addresses for host H1 and H2, we have the IPv6 addresses as well. So AAA, and then : : 1, and then BBBB : : 1. Okay, these are the IPv6 addresses for H1 and H2. Okay, so step 1, as usual, we will start the mini edit graphical user interface, and it's asking us for a password. The password is also here password. All the labs will have the same credentials, so it's gonna be password in all the labs, all small caps. Okay, and then we will load the topology for lab number 4. So this is already built. File, open, lab 4, and lab4.mn. Now that we have the topology there, which again is the same as the one that we used before, all we have to do is start the emulation by clicking on the run button here at the bottom of mini edit. The buttons are grayed out. It means this topology has started successfully. We will do the same starting point from the previous one. So we'll first open the terminal of the host H1, right click, and then terminal. And from there, I will issue a ping from H1 to H2. This is using the ping command. Just to make sure that there's nothing on the switch and we can't forward packets now. And we can see that there's no replies. So the switch is empty. There's nothing, there's no program on the switch yet. Now we will start with defining the headers that we want to parse in our program. Okay, And again, we will use the same environment. So we will go to the desktop and then click on the terminal icon. This is step number 1. And then step number 2 would be to launch the Visual Studio Code and pass to it as parameter the location of this specific lab, which is lab 4. Okay, so now we are inside the environment. We have also the same files, but we will check now the headers.p4 file, and we will see that it's empty. It only has few comments here. Our job in this lab is to actually fill this file here. Okay, so the first thing that we start with here in this headers.p4 file, we'll start by adding some type defs and some constants. Specifically, we're going to add the type def for the MAC address to be 48 and for the IPv4 address to be 32 bits. And these are type defs, so you can use bit 48, or you can just simply use MAC address _t for better readability of your program. And then you would have like a constant here, type _ IPv4, that has the value 800 in hexadecimal, or 800 in hexadecimal. Okay, so I will type these under the first command. Type def bit 48, then MAC address _t, then another type def for now the IPv4 address, so IP4 address _t, and then we will create this constant 16-bit, so const bit 16. The name is type _IPv4, and the value is 0x800. Okay. Now, step number 3, we will start by defining the header for the Ethernet. Okay, so we will do that under the Ethernet header command here, and I will be typing this header definition here, and basically this corresponds to the figure that we were looking at in the slides, right? So you have the destination MAC address, the source MAC address, and ether type. So you have to write them in that order. So header, Ethernet _t, and inside it we have MAC address. This is going to be our destination MAC, so the ST address. You can obviously call them whatever you want. You are not like forced to use the ST address. You can use destination MAC or whatever name you want to give to it. And then source address. So after these addresses, we have the ether type, which is 16 bits, so bit 16, and ether type. Okay. Next, we will define the header in step number 4 for IPv4. Okay, and we will do that below the IPv4 header. So it can be a little bit tedious to write all the stuff here. Typically, what you would notice whenever you start experimenting more and more with P4, you would have all these IPv4, Ethernet, IPv6, all of them will be already available. You just copy them and use them. But the nice thing about the programmability of the parser is that you can define your own header and your own protocol, you know, and so that's why here we are defining everything from scratch, because for a P4 switch, it doesn't understand what IPv4 is, right? You have to tell it what the IPv4 header looks like. You are instructing it everything. Like you have to assume that it doesn't know any of these protocols, Ethernet, IPv4, MPLS, or any of those. All right, so let us now type in the following for defining the IPv4 header. So header IPv4_T. And then we have 4 bits for the version. We have another 4 bits for IHL, the header lengths. And then we have 8 bits for the diff serve, 16 bits for the total length, another 16 bits for identification, 3 bits for the flags, 13 bits for fragment offset, and then you have 8 bits for the time to live, TTL, another 8 bits for the protocol. This is gonna tell us if you have TCP or UDP in the next layer. And then you have 16 bits for the header checksum. And finally, you have the IPv4 addresses. So we will use now the type def IPv4 address T, and then source address. And then we will use it again, but now for the destination address. For at this point, we are not planning to parse IP options. IP options can be a little bit complex to parse because it can have like a variable length. Hopefully, we will be doing that in the future libraries. Okay. So now we define the Ethernet, the IPv4. Next, we will create a struct for our metadata, but we will keep it for now empty. So I will write here below the metadata struct. So struct metadata. You can leave it empty. You can type in a comment here, empty, obviously. And then, most importantly, we have to group those headers that we intend to use. And we have to first instantiate those headers and group them into one struct, which we call headers here. So struct headers. And here we have Ethernet, so note how we are using here the _T because this is how we defined what the type is like, this header. And we are creating an instance of it, which is this Ethernet here. And then IPv4_T, and then IPv4. So now that we've done with this file, we have to make sure to save it by pressing on Control-S or File and then Save. Next, we move to the parser implementation, which should be written inside the parse.p4. Again, I just want to make it clear that you can actually write all this stuff, or everything that you are doing now, the headers, the parser, the ingress, egress, everything inside one file, the basic.p4, and it works well. But we just separated it for better visibility, and so that for first-time learners, they just go to the specific file and know what they are doing instead of having a very large file to deal with. Okay, so step one, we have to click on parser.p4. And basically, you can see that we already have here my parser there. The reason we already have it because it's kind of like a, most of the time it's going to be the same thing. So we will not modify any of those. And the reason is because the V1 model expects you to pass an instance of this parser here that has exactly these parameters, right? So in case you want to modify something, you might want to modify the names. For example, instead of HTR, give it a different name. But There's no reason to do it, at least at this point. Okay, so we will start first by our first state, which is the start state. This is where the parser begins execution. I will add here state start. And when we type in a transition and we give another state here, for example, parse Ethernet. So what happens is that I'm doing a non-conditional transition. So I'm not making any kind of conditioning here before we go to the parse Ethernet state. Okay, so I'm telling it as soon as you start parsing, go to a state that's called parse Ethernet. Now, where's that parse Ethernet state? You have to write it. Typically, it's a good idea to create a state for each of the headers that you are parsing. This is like a common practice, although not necessarily required to do it like this, but it's better so that you have everything separated. So now we will implement the parse Ethernet state. So I will write that below the command for the parse Ethernet. And this is gonna be state parse underscore Ethernet. And within that state, first we have to extract the headers, right? So this is done by using the extract method, which is provided with the extern packet. So packet.extract, and you specify here what are the headers that you are planning to extract. So if you write here, for example, header.ethernet, what happens is that the compiler will look at how big this Ethernet header is, and it can know that because we already defined the header. We specified, let's say, 48-bit for the destination, 48-bit for the source, and 16-bit for the ether type. So it knows how big that is. And you can think of it like a cursor, right? So start taking all these bits and then put it inside the header.ethernet so that you can use it later on in your program. So now that we have this header Ethernet extracted, we can inspect the ether type to determine what is the next protocol, whether it was IPv4 or IPv6 or any other protocol. Now, to do this, we're going to do a transition, but this time it should be a conditional transition. So we do this by using transition, and then we use a select statement. This select statement kind of have like a similar syntax to what you would write in a C language when you use switch, right? But the difference is you don't have break or anything like that. The idea here is very simple. I want to transition by after, I only do the transition after checking for whatever you write inside this select here. So in our case, we were gonna look at the header.ethernet.ether type. Okay, so we wanna do the transition, but only after looking at the value of ether type, which is found inside my Ethernet header. Now, if this value, so if the ether type is equal to type IPv4, which we defined in the headers, right, 0x800, then we will go to a state called parse IPv4. Otherwise, so we have a default here. Default means if none of the previous conditions matched, we will just accept. It means I only parse Ethernet and then I accept the packet. Okay. Now, we said here that we're going to go to the parse IPv4, but there's no parse IPv4 yet, so we have to define it. Okay, and this is step number 4. It's going to be here under the add the IPv4 state below. So state parse IPv4. And here we will also do the extraction, but this time this is gonna be for header.IPv4. And again, I can use those here, IPv4 and Ethernet, because this is what I combined in my structure header, right? In the struct that I created, we have Ethernet and we have IPv4. So that's why I'm able to using them here. And here, I will just do a non-conditional transition to accept. Okay. The next step would be to save the changes by using Control S or file save. Now we can test the program. Hopefully we didn't do any typo because we wrote a lot of small stuff. So P4C basic.p4. Basically, you have a lot of files here, but you only need to compile the main one, right? And because that main one is including all the other files, then everything will be taken care of. So it compiled successfully. We have an output, basic.json. This is going to be used for our switch. And as we did in the previous lab, after having this compilation successful, we need to push this output to our switch S1. And we will do so by using the push to switch script. We give it the file name, basic.json, and the script and the switch name, which is S1. It's asking us for a password. The password is password, all small caps.
So Eli, before you continue, just to highlight a few things that are pretty cool about P4 is that the switch is not aware of any protocol that's protocol independent, and you had to write IPv4 Ethernet. But the other thing is that there is nothing preventing you to keep parsing or build your own protocol or parse, let's say TCP or UDP. What are the limits when you work with these devices?
Yeah, so at the end, you can do as much parsing as the resources allow you, right? Typically, when you work on a software switch, you don't have that limitation. It's not a big problem, especially for this BMv2, because BMv2 at the end is a software switch. It doesn't matter much how much you can go deep inside the packet. But when you work with a hardware switch, for example, in Tofino, there you have some limits on how much you can go inside the header, how many bits you want to extract there. And the nice thing about Tofino, if you want to work with the hardware, is that their software version, which is the Tofino model, would be exactly the same thing as the compiler for the hardware. In other words, if you have an error complaining that you have some issue with the parsing or you have some issue in anywhere in your program, then this is the same error that you will get on the hardware. But if it's accepted by the model, it means that, okay, it's now going to work on the hardware. Now, how much we can parse, it depends on the architecture. And I mean, we can't give specific numbers, right? But I would say you can go a little bit. I mean, you can, a lot of applications, they parse TCP, and you can parse a little bit higher than that as well without any implications on the performance. All right. So now that we pushed our output from the compiler to the switch S1, we can proceed to verify the configuration as we did before. So this is going to be step number 5.2. So we will go back to our mini edit by clicking on the mini edit item here. And then we will go inside the P4 switch, inside the file system, by right-clicking and then hold the right-click and then terminal. So make sure to hold the right-click, because sometimes you issue a right-click and then it just pops up and disappears. So make sure always to hold it so that you can get through and launch that terminal. Again, we're going to make sure that our output is the compiler's output was pushed successfully. So we will use ls, which shows the current files or the files inside a certain directory. In this case, the current directory. You can see we have basic.json. Then we can use the command ifconfig also to see the interfaces as we did before. And we can see that we are using the same topology. So we also have S1 ETH0, S1 ETH1. Now, when you create your own topology, you might have, let's say, 2 P4 switches, 1 legacy switch. You might have an open flow switch. So you would see that the number of these interfaces will increase. It depends on how many links you have out of your switch. And I just want to mention that, especially like if you're interested in building your own topology, if you want to know which one of these interfaces correspond to which side of your switch or which link of your switch, you can go to the Mininet terminal. And this is the terminal that's already there when you launched MiniEdit. So in my case here, it's called shell number 1. And there you can simply type in links. And this is going to tell you that you have host H1, which has the interface H1-ETH0. It's connected to S1 ETH0. So we know now that H1 is connected to S1 ETH0. And then you can see that we have H2 connected to S1 ETH1. So we know now H2 is connected to this interface. And this is very important because when you have a bigger topology, you might have a lot of interfaces and you need to keep track of them so that you can program your data plane correctly. Okay. Next, we will start the daemon as we did before and allocate the interface and enable logging. So I will type in here this command, simple switch -i 0 at S1-ETH0. And then -i 1 at S1-ETH1. Nanolog IPC. And then the program name, which is basic.json. And of course, at the end, we can run it in the background. This is not necessary, but instead of having to open a different terminal for the switch, you can just simply run it in the background and then run another program on the same terminal. Okay. Then going to step number or section number 6.2. Step 1, just press enter to get the terminal back here. And here we are also pushing in step number 2 the table entries to the switch by using the simple switch CLI. There's a lab number 7, that will navigate through the simple switch CLI. We're going to do that next week. And this is going to show you all the steps you need so that you populate the tables manually. Okay, for now, we're just going to use a script that already has the rules. So this is lab 4 and rules.cmd.
Eli, there is one question, perhaps is a good point to answer this question because it's related to what you just said. How can we push the output of the compiler to the whole switch, more than one switch? That's number 1. Number 2, how can we see the content of the flow table? If you want to address those two.
Yeah, certainly. That's also a great question. Part 1, if you want to push to many switches, so far we just have this push to switch script that you basically pass to it as parameter the program and the switch name. So if you have, let's say, 5 P4 switches, they will have the name, let's say S1, S2, S3, S4, S5. You would need to execute that script 5 times. So push to script basic.json S1, push to script basic.json S2, and so on. We did it this way instead of pushing to all the available switches, only because more advanced applications might require different P4 programs in the same topology. One program might be doing maybe some caching, another doing load balancing. They have different data plane descriptions. Part 2, how can we see the content of the flow table? So this is precisely what you would do in the simple switch CLI tool. Okay, now the way we are running it, we are just passing to the standard input the content of this file, which already is there, but you can type in simple switch CLI without anything. You can go to the terminal there. It's like a command line interface where you can simply interact with the switch data plane. And there you have few commands to dump the table entries, or to delete, to insert, to update, and all these different kind of stuff. And this is what we're planning, like the next part of the workshop, which is next week. We're gonna go over this and show example of all these. And the third one is, which is the syntax of the rules.cmd. So you can simply like use VI or any editor here, Nano, if you want, to look at this file. So you can see here, I just wrote cat and then this file name, and you can see you have something like table add. You write the block name here, my ingress, the table name, and then the action name, and then the parameters. This is what we're gonna go over next week. But this is, for example, simply to add a certain entry to a certain table. Yeah, no problem.
What you are doing, at least playing the role of a control plane, for example, you are doing a static routing at this point, or
Yeah.
but that's what a routing protocol would do, or the administrator would do, to push down to the data plane.
Yes, exactly. This is all from the control plane, or if you have like a centralized controller, but you can't do these table adds inside the data plane, inside your P4 program. This has to be done externally, for sure. But yeah, definitely, like, this is something that you might run external algorithms that, like what we do in SDN, right? You might have an algorithm that will create the entries and then push them to flow tables. It's the same idea here. All right. Now step or section number 7, step 1, simply to start the Nano message client to see the log. And it's ready for us now to send packets. Next, we will go to host H2 and start the terminal and execute the receive script. And then on host H1, we will also open the terminal. I think it might be already open here, but you can always open 2 terminals for one host. It's possible. And then we will send 10.0.0.2. So send an IPv4 packet to host H2. And optionally, you can give it a certain payload to be inserted on top of the packet. Okay, so now the packet is sent out of host H1. If we inspect the logs of the switch, so this is in the behavioral model, we can see here that same thing that we saw in the previous lab. Packet entered, the parser executed, and it extracted the Ethernet and the IPv4. How did it know about that? It's basically by inspecting the Ethernet field, the ether type field of the Ethernet header, which is here IPv4, and that's how it knew that the next state would be for IPv4. Okay, and this script that we have here, send.py, is just using Scapy, a Python library, to craft a certain packet. You can tell it, I want, for example, Ethernet with these specific header fields. On top of Ethernet, I want IPv4 with these specific header fields, and so on. You can construct the packet however you want. Okay. Now, we're going to do some modifications just to augment the program to be able to parse IPv6. To do so, it's really simple. All we have to do is go back to our editor, and first we will go to the headers, and then, as we did for the IPv4, we can create a constant here to specify the type for IPv6 now. So const bit 16. And now we're going to call this constant type IPv6. And this is going to be equal to 86DD. Okay. And then we need to add the header definition for IPv6. So we will do it here under this command, and I will type in the code that we see here on the left-hand side. So this is header IPv6 underscore T. And then we have 4 bits for the version. We have 8 for traffic class. We have 20 for the flow label. Again, I'm getting this from how the standard IPv6 header looks like. Okay. And then 16 for the payload length. Payload length. And then we have 8 bits for the next header. We have another 8 bits for hop limit. And we have the addresses, which are these IPv6 addresses, 128 bits. So source address and bit 128 destination address. Obviously, here we could have created a type def for the IPv6, but we just did it with writing the bit and the number of bits in it. Okay. Next, we need to make sure to append the IPv6 header to our header structure, because we are basically planning to use that in our program, so, or to parse it. So this is gonna be IPv6 underscore T, and then IPv6. So we create an instance of the IPv6 type. Okay, after we do that, we make sure to save, Control S, and then we will implement the parser. So if we go back to the parser.p4, what we have to do here is when we parse the Ethernet, we want to look at the ether type, and based on the ether type, we will go to the IPv6 state, right? Or the parse IPv6. So all we have to do here is simply add. So beside the type IPv4, we will have a type IPv6. And this is going to take us to a state called parse IPv6. Okay. But now we don't have the parse IPv6 state, so we have to implement it in the next step. So state parse IPv6. And here we are extracting the IPv6 header. So header.ipv6. And then we transition to accept. Okay. Do we have a question, Dr. Jorge, before we proceed?
Yes, there is a question. Let me read for you. Eduardo, how is the first packet delivered from the host H1 to the switch? Does the switch has implemented ARP, address resolution protocol, and or ND, neighbor discovery?
Yeah, that's a great observation. Basically, what we did when you use this send.py script, which is basically you know, a SCAPI library on Python, you are crafting the packet, deciding exactly what the source IP, destination IP, source MAC, destination MAC, all these different kind of stuff. And because you are not using a tool like, for example, ping or iperf or any of those that will use the actual stack, and they are standardized, so they're going to go over the operating system and do that. You don't need here ARP implemented. But on top of that, the current program that we have is written in a way that it will look at the packet and see if it is from port 0, it passes it to port 1. And for port 1, it passes it to port 0. So if the operating system sends an ARP packet, this ARP packet will be eventually sent to the other device, and they will learn the addresses. And that's why if you try to issue a ping command, it still works here. Okay. The other alternative, like let's say if you have a table that matches on the destination IP, this is where you would need to process ARP. Otherwise, you have to hard code the values on the tables of H1 and H2 manually.
And I will just add to this, Ali, that's a great observation, because in a real deployment, we will need the ARP, right? But we're keeping it simple here.
Yeah, definitely.
In this library.
Yep, definitely. All right. So now after step 5, we added the parse IPv6. We saved the change, and we have to make sure now that we recompile, and this is because we modified the program. Okay, so we have to reissue the P4C basic. We can use the up arrow to retrieve the previous commands. And then again, we have to repush the output of our compiler to the switch. The password here is password. Okay, so we recompiled and we repushed the updated output of our data plane to the switch as well. Now, let's test this augmented program. So the first thing we have to do is go back to the terminal of the switch. And this is here in the Xterm behavioral model. What we have to do here is we have to stop the logging that we were running before. So you can use Control-C. This is going to interrupt the previous command. And also, we need to terminate the daemon of the switch, which is already running. And we can use something like pkill. This is going to kill the process of whatever name you give it. In our case, simple switch. So we're going to terminate that program, which is the simple switch. Okay. And why we are doing so again, because we recompiled, we have a new data plane description, and we have to reuse that new updated one. Okay, so I will use now the up arrow to restart the simple switch with the updated file, so that we retrieve the previous commands. Okay, this is it. Nothing has changed here. And then step 4, we just press enter to return back to the CLI. We push the rules. I will also use the up arrows here. For this one, the simple switch CLI. So I'm currently executing here. And then start the nano message client. And now what we're going to do is we're going to go to host H1 and send the packet to host H2. But this time, this packet is not an IPv4. This is going to be an IPv6 packet. And we created a script called send IPv6 just to make it a little bit easier, but it's really very easy if you want to play with those sending and receiving scripts, right? Instead of IPv4, you write IPv6. So send underscore IPv6, destination is BBBB and 1, and some payload. So the first thing to notice is that now Scapy is saying that we have an IPv6 address, okay, on top of Ethernet. So we have Ethernet. The type would now point us to the next header, which is IPv6. Now, if we go back to our behavioral model, the BMv2 switch, and see the logs, what we can see here is that, again, the packet was accepted on port 0. The parser started. We started with Ethernet, but because we had this value of IPv6, it knew that the next header is IPv6, and now it took us to the IPv6 parse IPv6 state, which extracted the IPv6 header. Okay, and you can think now that, okay, maybe I want to look at the TCP port or UDP port, and basically all you have to do is extend this parser, select on which field you want to use to determine what the next protocol is. For example, for IPv4, you have protocol field. You can use it and you can infer whether the next header is TCP or UDP or others. And you have to make sure that, of course, you define the headers and you implement that parser well. Now, once this parser works and you are sure that you are parsing these headers, then throughout your program later on, which we will see in the next part of the workshop, in the tables, for example, you will be able to use fields inside those headers. So you can, for example, say, I want to match on the destination IP of the IPv6 header. You can do so. Or you can even do something that is completely different than what you are used to in a regular switch. Maybe you want to parse on the TTL value, or you want to parse on some, I don't know, quality of service fields inside the headers or anything like that. So that's what makes P4 very powerful. You have this opportunity of, or possibility actually of doing processing on fields that are not typically used for a certain activity. You might want to forward based on, I don't know, the quality of service field, right? Yeah, and at this point, that's the end of Lab 4. Dr. Jorge, is there any question or?
Thank you very much, Ali. Let's see if there is any question. We're reaching the end of the first day. I don't see any question. Thank you, Ali. Thank you very much for the presentation.
Thank you.
Well, we're finalizing day number 1. I want to remind everyone that the workshop will continue next week, 1 p.m. Eastern time on Wednesday, February 23rd. The agenda is online. I want to thank you everyone for attending this first day. Jason, do you have any last comment for today?
Nope, I think today was very successful and hope everybody got a lot out of it. And we look forward to being able to continue next week.
All right. Well, thank you, everyone. I hope that you have a good rest of the day, and I will see you next week.